whether the system is stable or unstable, then you can use Rao-Hurwitz stability criteria to figure out whether the system is stable or not. Okay, so let me start with some basic ideas about stability. We have discussed stability in the previous lectures, so let's talk about those ideas. So remember I said that, let's say we have a second order system with mass m, displacement x of t, external force F of t, spring constant K, and damping constant C. Then we know that this system, we know that this system is the transfer function of this system, or the transfer function of this system is G of S is equal to 1 over ms squared plus Cs plus K. Okay, this is the transfer function of this system. So this is one form of the transfer. Another standard form in terms of omega n and zeta, the standard form will be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So just remember that this and this are not exactly equal. Okay, I've discussed that in the previous lectures. Now, if we have this transfer function, let's suppose the numerical values for mass is, let's suppose 1, C is 2s plus K is, let's suppose 3. Okay. Now, if someone asks you if this system is stable or not, if someone asks you if this system is stable or not, okay, you can apply different criteria, or you can, so on the physical level, you can check whether this system is stable or not by giving it some small disturbance. Like, let's say we give it some small initial displacement, x of t equal to 0 equal to 1 centimeter. A very small initial displacement. So I just press it about 1 centimeter. I press the mass down about 1 centimeter and then let it go. If I let it go, what will happen? That it will start oscillating and since the system has a damper, so gradually the amplitude of oscillation will reduce and eventually the mass will stop oscillating. Now, based on this response, as I see, when I give this system some finite input or a bounded input, when I gave a bounded input to this system, the response of the system was also bounded, means that the response didn't approach to infinity. ठीक है, ऐसे तो नहीं हुआ ना कि when I gave it some 1 centimeter displacement, as a time increased, the amplitude of oscillation kept on increasing and eventually it approached to infinity. That will be an unbounded response. That was not the case. On the contrary, what happened then when I gave a bounded input to this system, the system response was also bounded, means it didn't approach to infinity as t approaches to infinity. Then, based on this physical behavior that I observe, I can say that the system is stable. Okay? That the system is stable. If I had given a bounded input, a finite input to this system, and the system response approached infinite value as t approaches to infinity, in that case, I would have said that the system is unstable. But that is not the case for this physical system. So I'm going to say that the spring mass damper system is inherently stable system. Now, so this is how you physically determine whether the system is stable or unstable. What if you don't have the physical system? You only have the transfer function of the system. You only have the transfer function of the system or the governing equation of the system. How can you then determine if the system is stable or not? Okay? In that case, what we need to do is we need to get the characteristic equation of this system. And characteristic equation is the denominator polynomial equated to denominator polynomial of a transfer function, denominator polynomial of a transfer function equated to 0 gives us the characteristic equation. So this is our characteristic equation for this transfer function. This transfer function is for this physical system. Now, if you find the roots of this characteristic equation, and plot them on the complex plane, let's call it, this is real positive and this is imaginary positive. So if I plot it on the complex plane, so this whole plot is called complex plane plot. If I plot it on the complex plane, let's suppose the roots comes out to be S1 is equal to -2 plus 3 iota, and S2 is equal to -2 minus 3 iota. You can just look at the roots and tell if the system is stable or unstable. You can plot the roots on the complex plane, -2 and +3 and -3. So these are the roots. So you can either look at these roots, S1 and S2 values, and if their values have negative sign, then this means that the system is stable. If these real values have positive sign, this real value have positive, if somebody is messaging me, I'm sorry, I'm not able to see the messages when I'm presenting. So I would suggest if you can, if you don't have an issue, and you can basically speak to me rather than sending a message. Okay?
So there is no message here.
अच्छा ठीक है ठीक है. You are able to see my presentation?
Yes, sir.
Okay. So if you look at the roots here, this roots, I'm talking about these roots. If you look at these roots, you can tell whether the system is stable or not. So if there is a positive sign for the real part of the roots, then the system is unstable. If there is negative sign, then the system is stable. If the system only have two roots and it doesn't have a real part, or the real part is equal to 0, then the system is marginally stable. So you can, now so far we have discussed that if you have a system, a physical system, you can tell whether the system is stable or unstable by giving it a bounded input and observe the response of the system. If the response of the system approaches to infinity as time t approaches to infinity, then the system is unstable. Otherwise, if the response of the system decay as time t approaches to infinity, or decay to 0 as time t approaches to infinity, then the system is stable. if the system response neither decay nor grow as time t approaches to infinity for a bounded input, then the system is marginally stable. So हमारे पास stability की 3 sub criteria हैं. Number 1 is unstable. Number 2, stable. Number 3, marginally stable. Physically, how would you tell if the system is stable? If you give a system a finite input and its response approaches to 0 after some time, or when time t approaches to infinity, then the system is stable. If its response approaches to infinity when time t approaches to infinity for a bounded input, then it is unstable. If its response neither decay nor grow as time t approaches to infinity for a finite input to the system, then the system is marginally stable. Okay? Now, this is when you have the physical system. This is when you have the physical system. But what if you don't have the physical system to test it? Okay, you only have the mathematical equation of the physical system or the transfer function of the physical system. Then how can you tell whether the system is stable, unstable, or marginally stable? The answer to that question is that you find roots of the characteristic equation, which are also known as poles. And if the poles values have positive real values, then the system is straightforward, unstable system. If the real values have negative, if the poles have negative real values, then the system is stable. If the poles are only 2 in number and they have 0 real values and some imaginary values, then the system is marginally stable. On the complex plane, how can you tell if the system G? Question? Tanveer? G? Okay? Okay, I'll check it again. Okay.
सर आ रही थी आपकी प्रेजेंटेशन नजर आ रही थी सर.
अच्छा, अब खैर दोबारा चेक कर लें. तनवीर अब नजर आ, ठीक है. अच्छा, so we can also tell whether the system is stable. So far we have discussed 2 ways to find the system is stable or not. Number 1, physically testing the system by giving it a bounded input or finite input and checking the response of the system as t approaches to infinity. Second, if you have the governing equation or the transfer function of the system, you have to find the characteristic equation of the system, and then from the characteristic equation you find the roots of that characteristic equation, and then you observe the real part of the roots of the characteristic equation. If the real part is positive, the system is unstable. If the real part is negative, the system is stable. If the real part is 0 and they are two complex poles, then the system is marginally stable. Also, you can plot these poles on the complex plane, and based on their location on the complex plane, you can tell whether the system is stable or unstable or marginally stable. So if the poles are in the left-hand side of the complex plane, then the system is stable. If the poles are in the right-hand side of the complex plane, then the system is unstable. If the poles are on the imaginary axis itself, there is an additional criteria. We will study that in today's lecture, but for now, if the poles are on the imaginary axis, they may be marginally stable or they may be unstable, and we will study now when they will be unstable and when they will be marginally stable. By marginally stable system means that the system response doesn't decay, the system response neither decay nor grow as t approaches to infinity for any bounded input. ठीक है, यहाँ तक clear? Any questions, students?
So what does marginally stable means in the physical system?
In a physical system, a marginally stable system, for example, for spring mass damper system, if there is no damper, that means what will happen if there is no damper? What will happen to the response of the system as time t approaches to infinity?
It will keep moving. There will be no decay.
There will be no decaying, and the system, and of course there will be no growth for a spring mass damper system. So this is called a marginally stable system.
Okay, all right.
ठीक है, it is marginally stable क्योंकि अगर ये बिल्कुल दरमियान में है ना, it is neither growing nor decaying. If the response grows with time, then the system is unstable. If the response decay with time, then it is stable. Since it is not decaying, so therefore it is not unstable. Therefore it is not stable. And since the response is not growing, therefore it is not unstable. It is between stable and unstable. So we call it a marginally stable system.
Okay, got it, sir. Thank you.
Okay. So now let's move forward with the lecture. For a linear time invariant system, okay, lecture 1 of this lecture. Linear time invariant system. A system is stable if the natural response approach to 0 as time approaches to infinity. ठीक है, natural response की बात करें. Natural response कैसे हमें पता चलता है? You give a system some initial displacement or some initial condition, and then let it go. जैसे अभी स्प्रिंग मास डैम्पर सिस्टम में हमने इसे इनिशियल डिस्प्लेसमेंट दी थी 1 सेंटीमीटर, and then let it go. You don't apply any external force after time t is equal to 0. This type of a response is called natural response of a system. So if you give some initial condition to a system and observe the response of the system, and then observe the response of the system after time t is equal to 0 up till time t approaches to infinity. If the response approaches to 0 as t approaches to infinity, then the system is stable. If the response approaches to infinity as t approaches to infinity, then the system is unstable. If the response neither decay nor grows as t approaches to infinity, then the system is called marginally stable. The same definition that we discussed in the previous slide. Okay, so why does that happen? Okay. For example, if we have this poles, S1 is equal to -2 plus minus or plus 3 iota, and S2 is equal to -2 minus 3 iota. Let's assume we have a physical spring mass damper system which has 2 poles. Pole number 1, which is S1, is equal to -2 plus 3 iota. Pole number 2, which is S2, which is equal to -2 plus -3 iota. Now, we know that the real part, when we plot the response of this system, when we take inverse Laplace of x of s, we get x of t is equal to e raised to the power -2t plus something, e raised to power something, cos into something and something. We are concerned about this. The real part, see, if we have -2 here, what will happen? That as t approaches to infinity, this whole term will approach to 0 because of -2. But what if we have a positive 2 here? Then in that case, as t approaches to infinity, then x of t will approach to infinity. So that means that the stability or the response characteristic, whether it approaches to infinity, st approaches to infinity for natural response, or it approaches to 0, st approaches to infinity again for natural response, depends solely on the real part of the poles. So if the real part are distinct, now for any transfer function, there are three possibilities for the roots. That the roots are real and distinct. Roots are real and repeated. Actually, four possibilities. Roots are complex and distinct, and roots are complex and repeated. Now, what are the, can I write the four examples for you? Let's see. New slide. For example, I have g of s equal to 1 over s plus 1 into s plus 2. Now these two roots, the poles for the systems are real and distinct. Can any student tell me what does this mean? Is this, if this, does this, is this system overdamped, critically damped, underdamped, or undamped system? Any student? Can someone tell me?
It is overdamped.
Yes, very good. So this is an overdamped system. The roots are real because first root is equal to -1 and second root is also equal to -1. Real, but they are repeated. So what kind of system is this? Is this one?
Critically damped.
It is critically damped. Very good. When the roots are real and repeated, then it is critically damped. Okay? Now, let's suppose I have these roots. S minus 2 plus 3 iota, or S minus 2 minus 3 iota. You can also have this in the form of S minus 2 plus minus 3 iota. It's the same thing. Okay? So right now, can somebody tell me what are my roots? Are they real or complex roots? Students?
Complex.
So they are complex because you can see there is iota in both the roots. So they are complex roots. Okay. Are they repeated or distinct?
No, they are distinct.
They are distinct because one is plus 3 iota, the other one is minus 3 iota. So they are not the same value. So they are distinct. Okay? Okay. But what if, so for the fourth case, I need a fourth order system. So let's suppose I have S minus 2 plus 3 iota into S minus 2 minus 3 iota. Again, S plus 2, sorry, S minus 2 minus plus 3 iota and S minus 2 minus 3 iota. So, again, are the root complex or real? Students?
Complex.
They are complex. Are they repeated or distinct?
Repeated.
Good. So they are repeated. So these are the four cases of roots. And those 4 cases corresponds to the fourth condition of a second order system. So, so not this one, because this is a fourth order system. These 3 correspond to the 3 condition of a second order system. Number 1, real and distinct means overdamped system. Real and repeated means critically damped system. Real, complex and distinct means underdamped system. So let's come back to our system, to our slide. See, if we have real and distinct roots, then x of t. So for example, I have S1 is equal to minus 2, S2 is equal to minus 3. Then x of t will be equal to e raised to the power minus 2 plus e raised to a, e raised to the power minus 2 plus b, e raised to the power minus 3t. You can see as t approaches to infinity, these 2 terms approaches to 0. Therefore, we can say that as t approaches to infinity, then x of t approaches to 0 when limit t approaches to infinity. So this system is stable. If the system is, let me show you another slide somewhere here. Just give me one moment, please. Lecture 2. Okay. In one of lecture 2, we have discussed, let me bring that slide up for you. So let me stop sharing and then I'll share the next one for you. Okay. Start sharing window. And so are you able to see the calculation slide?
Yes, sir.
So if you can see that if we have 2 complex poles, then the final solution is 2e raised to the power minus sigma. This is the real part. Okay, the real part. So 2e raised to the power a, which is a constant, into cos omega t minus phi. So this portion is responsible for oscillation. Okay, and this portion is responsible whether this oscillation decay with time or this oscillation grows with time. Clear? Students, this is a very important point. Yes, बात को आपने समझना है, ठीक है? So whenever you have complex poles, so for example, this is a second order system with 2 complex poles. So this is your S plus 2 minus 3 iota, and this is your S plus 2 plus 3 iota. Okay? So your response will be equal to your x of t, or the response for this system. Let's make it x of s. So x of t will be equal to so this is some value. Okay? Let's make it a, or let's make it b, e raised to the power minus 2t plus b cos. Now omega, we know that omega, so we can find out that omega into t minus phi. Now b omega into t, Okay. Okay, so this basically becomes B. ठीक है? Minus 2 correspond to this. Okay, so this minus 2, e raised to power minus 2 corresponds to the real part of the root of the pole of the transfer function. Now, if the real part is negative, which in this case is where s is equal to minus 2 plus 3 iota, and s is equal to minus 2 minus 3 iota. Okay, since the real part is negative, therefore we have a number of E. This negative power of E will gradually decay the response of the system. And because of that, the system response will eventually approach to zero as time t approaches to infinity. But if the
पोल्स में
जी
तो नहीं होगा सर
पोल्स क्या होगा
पोल्स में 2 का नहीं होगा सर ये ट्रांसफर फंक्शन का जो पोल है सर
हाँ
सर ये -2 नहीं होगा सर s -2 minus 3 iota और s -2 plus 3 iota
नहीं this will be minus plus होगा क्यों then s is equal to -2 minus 3 iota. समझा रही सिस्टम का if it is लुकमान if it is s plus 1 s plus 2 देखिए माइनस आ जाए फिर क्या होगा और s is equal to sorry plus 1 इसका मतलब the is in the right hand side of the complex plane and the system is unstable. Let's suppose if I have a x of s is equal to 1 over s plus 1 into s plus 2. What will be x of t for this system will be something like a into e raised to the power minus 1 of t because s1 is equal to minus 1. plus b e raised to the power, depending on what kind of input is, assuming it's some initial disturbance, so the input would be the response would be something like this. So S2 is equal to -2. So -2t. But what if the system poles are identical? Then the response will have, of course, it will be -1, but there will be t. ठीक है? ये t क्यों आया? Student?
Because there are
S plus
two the same.
Because it is repeated. ठीक है? For example, if I have, let's say, +1 into s plus 2 into s plus 3 into s plus 4, then my system response would be of the form of exactly will be something like this. X of t is equal to a e raised to the power -1 of t for this pole plus b e raised to the power -2 of t for this pole, c e raised to the power -3 of t for this pole, and then for any repeated pole, it will be C3t. Okay? If we have, this is for this pole. If we have one more pole, S plus 3, which is again repeated, then it will be, response will have e raised to the power, e t square, e raised to the power -3t. Is it clear, students? Partial fractions में आप लोगों ने किया हुआ है.
Yes.
ठीक है? So for example, if I have a system response something like this, a e raised to the power -4t plus b t e raised to the power -4t plus c t square e raised to the power -4t. इसका क्या मतलब है? इसको देख के ये t वैल्यू और t square वैल्यू देख के आप मुझे क्या बता सकते? What can you tell me about this system poles?
There are three identical poles.
There are three identical poles. अगर एक t होता तो इसका मतलब है कि ये दोनों आइडेंटिकल है, क्योंकि यहाँ पे t स्क्वायर है, इसका मतलब है कि ये तीनों, वो तो खैर आपको यहाँ से भी पता चल रहा है, ठीक है? But t square basically tells you that there are repeated poles. Okay? Now, the same scenario is, now we have the same scenario for complex pole. जैसे real poles में repeated poles हो सकते हैं और उसमें t की addition होती है. Same is the case with complex poles. S plus 2 minus 3 iota and S plus 2 minus plus 3 iota. For this case, x of t will be equal to a e raised to the power minus 2t, that is because of this, 2t cos omega t minus phi. Okay, and so this is the response of the system. But what if I have two non-repeated? So s minus 3 plus 4 iota and s minus 3, sorry, let's make it plus, otherwise the system will be unstable. S plus 3 minus 4 iota. Then the system response will be plus b e raised to the power minus 3t into cos omega t. In this case, this is omega 1t, this is omega 2t, minus phi 2. This is phi 1. So this would be the response of a fourth order system with two sets of complex conjugate pair, but both the complex conjugate pairs are real and distinct. So these four poles are complex and distinct. ठीक है? कोई भी दो poles identical नहीं है. But what if my poles are complex and repeated? Plus 2 plus 3 plus 2 minus 3. Now we can see that these two poles repeat, okay, and these two poles repeat or are the same. In this case, my response will be exactly the same, except I'll add a t here. Okay. Clear, student? Students?
Sir,
Gigi,
why we
please.
are using one term for the two roots? In the real roots, we are using two terms. That is,
Because this term actually contains two terms. Ye, if you remember your FAC cos theta, cos alpha minus beta formula, you can expand it. Okay? You can expand it into two terms. So यहाँ पर, if I go back to this slide, let's go and discuss this slide. See, here we have two terms here, or two terms here. See, these are two terms. Then ये slide मैंने इसीलिए lecture notes, ये आपके chapter 2 के जो slides हैं उसमें ये slide मौजूद है, ठीक है? So eventually what we do is we combine, so we have one term which is 2 e raised to minus sigma t into a cos omega t. This is term 1. Yeah, and the second term, this multiply this, is the second term. But then we use trigonometric identity to combine these two terms into a single term. Does that answer your question, student?
yes, sir. And sir, why we are not mentioning the number that is written with iota, 3 iota, 4 iota?
Okay, so that is basically omega. समझ आ रही student?
Yes, sir.
ठीक है? So your iota is omega. So 3 iota, there will be 3t. If it is 4 iota, then it will be 4t, and so on. Is it not? Okay. Is it? So it is clear so far, huh? Now let's talk about special case. Marginally or marginally stable case. So let's suppose I have a system like this. S plus 0 plus 3 iota, and s plus 0 minus 3 iota. So if I plot these poles on the complex plane, real positive and imaginary positive, that's 3 iota and plus 3 and minus 3. Now both the poles are complex poles, or actually imaginary poles. They are on the imaginary axis itself. So their real part is equal to 0. For this type of situation, of course, my system response will be equal to a e raised to the power 0t cos 3t minus 5. Since minus 5. That means that the response of this system neither decay nor grow. Because the system response decay if this is minus some value. The system response grow if it is plus some value. The system response will neither decay nor grow because e raised to the power 0t is always equal to 1 for any value of t. So the system will just oscillate as a cos function with an amplitude equal to a. Clear है यहाँ तक students? Okay. Now what I'll do is S. So I'll just now you understand that real part here is 0 and s minus 3 iota. Now if I have repeated poles, s, let me write it the whole so there is no confusion. So s plus 0 plus 3 iota, s plus 0 minus 3 iota, s plus 0 plus 3 iota, s minus 0 minus 3 iota. What does that mean? That it is a fourth order system. It's a fourth order system. Okay. And the 4 poles are complex and identical. So we already have 1 pole and 2 pole at plus 3 and minus 3, and we have another pole at plus 3 and another pole at minus 3. So the roots are, or the poles are, complex and repeated. To be more precise, the poles and repeated, because they do not have real part of the complex number. Now in this case, our response will be equal to a e 0t cos 3t minus 5. In this particular case, the response will have another term plus b e raised to the power 0t for these 2 poles, cos t cos 3t minus 5. ये t क्यों आया? Any student?
Repeated root, sir.
बिल्कुल, because these 2 are repeated roots of these 2. ठीक है? Now, if for the 2 non-repeated imaginary poles, in this case, when there were only 2 non-repeated imaginary poles, the system's response approaches to 0 as t approaches to infinity. But this new case, this term will approach to 0. This term will approach to 0 as t approach. Sorry, this term will remain constant. Okay, let's call it constant oscillation. Constant amplitude. They will have constant amplitude oscillation. Okay, but this term, because of t, as t approaches to infinity, this term will approach to infinity, and this will make this whole term approach to infinity, and infinity plus some constant value. So constant plus infinity will be equal to infinity. So this means if you have only non-repeating imaginary poles, then the system is marginally stable. It is oscillating with a constant amplitude for any value of time t up till time t approaches to infinity. But if you have imaginary if you have repeated imaginary poles, then the system response will approach to infinity as t approaches to infinity, even for a bounded input. Clear है यहाँ तक? ये बात मैथमेटिक्स से क्लियर है?
सर ये सिर्फ तब होगा जब रियल पार्ट 0 होगा,
जब तक रियल पार्ट 0 होगा.
So it will be unstable.
Then it will be unstable. Yes. So remember मैंने आपको क्या कहा था? If the poles are in the right hand plane, then the system is unstable. If the poles are in the left hand plane, then the system is stable. If the poles are on imaginary axis, then it might be marginally stable or it might be unstable. Now you know how do you find out if the system is marginally stable or unstable if the poles are on the imaginary axis themselves. Clear है यहाँ पे?
yes sir.
ठीक है? So even let's suppose I get 4 poles. Okay, so if I get 4 poles, so I have 2 poles here, 1, 2, and another 2 poles here, 4 and -4. Now, is this system stable, unstable, or marginally stable?
Stable.
नहीं, stable तो नहीं है. Stable तो तब होगा when the poles are they are not to the left hand side of the imaginary axis. They are on the imaginary axis. So is it stable or marginally? So there are only 2 possibilities. Is it unstable or marginally stable?
Marginally stable.
Why is it marginally stable?
Because the poles are not repeated.
Because the poles are not repeated. So the response will be equal to a e raised to the power 0t cos pt minus phi 1 and plus b e raised to the power 0t. There is no t term here because they are not repeating. So when t approaches to infinity, this become equal to 1, and this also become equal to 1. So our final x of t becomes a cos 3t minus phi 1 plus b cos 4t minus phi 2. So as you can see, when t approaches to infinity, cos जो है तो cyclic function है. Cos and sine are cyclic function. So as t approaches to infinity, the cos and sine function will not approach to infinity because they are cyclic function. No matter what value as an argument you give to a cos function, its value will always remain between 0 and 1. Its value never approaches to infinity. Clear? Students?
Clear, sir.
Okay. So if the poles are in the left-hand plane, for real, ये आपने खुद पढ़ लेना. बस मैंने I've explained it. This is the mathematics of what I've explained to you. ठीक है? If the poles are in the left-hand plane, it is stable. If the poles are in the right-hand plane, they are unstable. if the poles are on the imaginary axis, they might be marginally stable if they are non-repeating imaginary poles, and they will be unstable if they are multiplicity greater than 1, they are repeating. Okay? If they are repeating imaginary pole, if they are repeating imaginary poles, then it is unstable. If they are non-repeating imaginary poles, no matter 100 or 50 or so and 1 million, if all, let's suppose a system has 1 million poles, and all the 1 million poles are on the imaginary axis, and none of the 1 million poles are identical to. If out of the 1 million poles on the imaginary axis, if 2 poles are identical to any other 2 poles out of the 1 million poles of the imaginary poles, then the system is unstable. Clear यहाँ तक?
Yes.
Students? Okay, now let's talk about, so you can tell the stability of a system. ठीक है? Clear यहाँ तक? Now let's go to,
Sir,
जी.
sir, what does phi means there in the equation? Phi.
Phi means is a phase difference. Phase difference. It comes out from this formula. Stop and it comes out from the formula. Let me go back to the slide. See, we have a formula that says that if A cos omega t plus B sine omega t, this is equal to C cos omega t minus phi. ठीक है? Where C is equal to A square plus B square, and phi is equal to tangent inverse B over A. ठीक है?
Yes, sir.
अच्छा. Okay, now let's go back. Okay, now you know, okay, up till now in the lecture, you know how to find the stability of a physical system. You know if the poles of the physical system are in the left-hand plane of the complex plane, then poles are in the right-hand plane, then the system is unstable. If the poles are on the imaginary axis, then the system might be marginally stable or the system might be unstable, depending if there is any duplicity, if there is any multiplicity of poles on the imaginary axis. Okay? This is your basic understanding of stability. But in today's lecture, we will study stability problem in a slightly different context. And that context is, I have a system like this. So let me add a slide here. Let's suppose I have a system like this. So positive, negative, this is R of S, and this is K, and this is 1 over S plus 2S plus 3. And let's suppose this is C of S. Now we know, so can anyone tell me what would be the roots, what would be the poles of this system, the transfer function? ठीक है, इसके poles क्या होंगे? S is equal to minus 2 plus minus. Can somebody quickly calculate it for me? 12 divided by 2. So this will be 16. So I think it comes out to be minus 1 plus minus 1 iota. ठीक है, कोई गलती तो नहीं कर रहा स्टूडेंट्स? Students? Anyone? Can you listen?
Yes, sir.
ठीक है. Okay. Now, if my roots are minus 1 plus minus 1, that's 1 comma 2. Question number 1, is the system itself, the encircled system, is the system or is the plant itself? This is a plant transfer function. If the plant itself okay, plus minus under root 2 आएगा.
Root 2 आएगा.
1.41.
अच्छा 1.41. चलो, doesn't matter. So again, answer the. Can anyone answer the question? Is the system is the plant with the roots minus 1 plus minus 1.4 iota, is it stable or unstable? The plant itself.
It's stable.
It's stable. Why? Why is it
The
stable?
real part is negative.
Real part is negative, or the roots are in the left hand plane. ठीक है, -1 और ये जो है +1.4 -1.4. Clear? ठीक है? So the plant itself is stable. ठीक है? Now, can you convert this whole system, not the plant, can you convert this whole system into a single transfer function? Anyone?
Yes, sir, we can try.
Yes. What will be that transfer function? It will be K S. क्योंकि ये दोनों series में ना, these two are in series. So
Yes, sir, we will multiply.
you can simply multiply 1 with K. So our transfer function will be G of S divided by 1 plus, because it's a negative feedback, 1 plus G of S into H of S. Now H of S here is simply 1. So
Yes.
we don't need to write 1. So our transfer function simply becomes, for the whole system, for the whole feedback system, our transfer function will become A over S squared, sorry, this is squared, A over S squared plus 2S plus 3 divided by 1 plus K over S squared plus 2S plus 3, or it comes out to be K over S squared plus 2S plus 3 divided by S squared plus 2S plus 3, S squared plus 2S plus 3 plus K. Okay? That comes out to be, now this is of course can be written as K divided by this, so I can cancel out these two, and my final transfer function will come out to be K divided by S squared plus 2S plus 3 plus K. Clear यहाँ तक? Student?
Clear, sir.
ठीक है? So after doing all those calculations, I'm just going to write it here. I'm just going to write the plant transfer function and the system transfer function, both of them side by side. So let's G1 be the plant transfer function. So or G be the plant transfer. G of S is equal to K over S square plus 2S plus 3. And T of S be the closed loop feedback control system transfer function. Now the system transfer function is equal to K over S square plus 2S plus 3 plus K. Okay? Can you see the difference between the two transfer functions? And this is only for the case when H is equal to 1. For a simple case when H of S is equal to 1. If H of S would have some other value other than 1, then it would be, this thing would be a lot different than this thing. Okay? But for now, we are considering the simple most case. Now find the roots of this transfer function. Find the roots of this transfer function. The roots of this transfer function will be minus 2 plus minus 4 minus 4 into 1 into C value is 3 plus K, where K is just a constant, okay, a variable, okay, 3 plus K divided by 2 into 1. So can we find out the roots if we do not know the value of K? So हम root की numerical, can we find the numerical value of the root without knowing the numerical value of K? क्या हम मालूम कर?
No, sir.
नहीं कर सकते. Okay, that is one thing you have to keep in your mind. The other thing is, if somebody asks me, okay, we know that the plant is stable, but is the whole system stable? We know that the plant is stable. Whole system stable. Whole system की stability मालूम करने का तरीका वही है. You need to find the poles of this characteristic equation, but we cannot find the poles of this characteristic. Okay? Now assume that is problem number 1. Usually we do not know the value of K. We know the range of K, but we do not know the exact value of the K. Sometimes we know it, but most of the time when we are designing a system, we
Sir, what does T of S?
T of S
Sir, what does T of S show?
is the transfer function of the whole system, of the feedback control system का transfer function, जो कि अभी थोड़ी देर पहले मैंने calculate किया था.
Okay, sir.
Okay. Now, assuming, let's say for sake of simplicity, let's say K is equal to 1. Let's say K is equal to 1. Then our roots will be equal to minus 2 plus minus under root minus K is equal to 1. This is 1. So minus 4 multiplied 4 divided 2. So this will be minus 2 plus minus under root plus minus under root 12. So
So it will be the same as we before.
no, it will not be the same.
Oh, once K. Oh, okay. All right.
Okay. So that means, can anyone tell me किसके पास calculator है? This value. Can anybody tell me this value? Calculate करके. Under root 12 divided by
1.73.
So it will be 1.73 iota. Plant के roots कहाँ पे? If I plot both of them, plant के roots जो हैं -1 और -1.4 पे, ठीक है, -1 and +1.4 -1.4, ठीक है, और ये माइनस यहाँ पे, these are the plant roots, ठीक है, और plant poles, जबकि इस पूरे सिस्टम के पोल्स कहाँ पे हैं? They are at -1 and ±1.7. They are here actually. ठीक है, यहाँ तक क्लियर है?
Yes, sir.
So what if I take k is equal to 10? What will happen here? k की वैल्यू क्या हो जाएगी? 10 हो जाएगी. यहाँ पे क्या आ जाएगा? 3 plus 10 is equal to 13. 14 multiply 3 plus 10. This value will be something greater. Let's say 5 ±5 iota. So what is happening when we are increasing the value of k? What is happening to the poles, closed loop system poles? They are moving. They are moving in a complex plane. Do you get the point, students?
Yes, so the imaginary part is increasing.
Yes. As we are changing the value of k, as we are really changing the value of k in the closed loop feedback system, in the closed feedback system, if I change the value of k, then the pole location changes. For the pole location doesn't change for g of s. G of s के poles पे कोई फर्क पड़ रहा है? If I change the value of k, if I change it, g of s के poles की location पे कोई फर्क पड़ रहा है? नहीं पड़ रहा. But if I change the value of k, g of s के poles की जो location है, that changes, because t of s has k in the denominator polynomial, जबकि g of s only has k in the numerator polynomial. ठीक है? And since pole value depends on the denominator polynomial, therefore k doesn't affect the pole position of the plant, but k affect the pole position of the closed loop system transfer function poles. Is it clear?
Clear, sir.
Okay. Now, if this path, as I increase value of k from k0 to infinity, if I trace this path, I'll get a path something like this. This path is called root locus. Locus means path. Locus means path. Okay? This is your next topic after steady state error. This is your actually last topic before we will study the controllers. Okay? So everyone gets the point. And I'm kind of explaining the root locus as well. What is root locus? If you have a plant transfer function like this, and you place it in a feedback closed loop control system loop, then the response of this feedback control system loop containing the plant transfer function, it depends on k value, because k value here will affect the poles of the closed loop feedback control system. It will affect the poles location of the closed loop feedback control system. Now, even though if the plant is stable by itself, and you place this stable plant transfer function in a closed loop transfer function, and then change the value of k, then the response of the total system may become unstable for certain values of k. ठीक है, कुछ सिस्टम का ये जो भी हमने रूट लोकस प्लॉट किया है, ये जो हमारा सिस्टम है, इसका रूट लोकस ये है. This is our initial plant poles. The closed loop feedback control loops poles move in this direction, up and down. Okay? But they never crosses the imaginary axis. But there will be some system whose plant poles are stable, like here, but when we increase the value of k, eventually the poles of the closed loop feedback transfer function will start moving in following this path, and eventually it will cross the imaginary axis at certain value of k. At certain value of k, it will cross the imaginary axis and the system will become unstable. This whole system will become unstable. Plant is stable because changing the value of k doesn't change the poles of the plant. But changing value of k changes the poles of the closed loop feedback control system. And there is a possibility that for a certain value of k, the system may become unstable. Do you get this point, students?
Yes.
Sir, it would be nice if you repeat this one.
Okay, what I'm saying, so let's look at it. Let's look at it from a different perspective. Let's say I have a system, a plant, which is k over s square s minus 3 s minus 4. ठीक है? Question number 1. Is this plant stable or unstable?
It is unstable.
Because S1 is equal to plus 3 and S2 is equal to plus 4. If I plot it on the complex plane, so if I plot it on the complex plane, it is 3 and 4. ठीक है? Now this system, G of S, sorry, this plant transfer function, this is unstable. No matter what value of k I use, for k greater than 0 to from k greater than 0 to k equal and k equal and less than infinity, the system is unstable. यहाँ तक clear है? Question, student?
Yes, sir.
ठीक है? Now let's put the system in a closed loop control system. So this is C of S. Unity feedback control system. Sorry. Put it here. ठीक है? Let's, for now, this is my controller. Actually, this is our controller. ठीक है? This is a proportional controller. This is your simple proportional controller, PID, proportional, integral, and derivative controller. So it's a sum of 3 controllers. Okay? So right now we are only using a proportional controller. if I use a proportional controller, then for value of k, as k value is, for value of k greater than 0, these poles will move in this direction. This we are talking for the whole system, पूरे system की बात कर, and then they will move something like this. ठीक है, इस यहाँ तक बात की समझ आ रही स्टूडेंट्स?
Yes, sir.
कैसे?
Sir,
Let me go.
बता दीजिए।
Let me go a little bit further. So this will become s square minus minus 12s, no, sorry, minus 7s and plus 12. Okay. Now, if I find, so g of s for this system is 1 over s squared minus 7s plus 12. And t of s, पूरे system का transfer function. Plant का नहीं, this is our g of s. And t of s is for the whole system. T of s will be equal to a g of s divided by 1 plus a g of s into h of s, which is equal to 1. Okay? When I find the transfer function for the t of s, it comes out to be, a little while ago I did the whole calculation, but it will come out to be s squared minus 7s plus 12 plus a. Okay? Now if I plot, now these are the roots of t of s are called closed loop poles of system, while the roots of g of s are called plant roots or poles. Okay? Now our system g of s was unstable. Now there are two reasons why we use controller. Reason number one, we want to make the system stable. Reason number two, we want to so reason number one, we want to make the system stable. Reason number two is we want to improve the performance of the, to make this system stable by introducing a proportional controller. Okay? Cascade controller means a controller in series. Now, as you can see, when I introduce this proportional controller, then the closed loop poles start, as I increase the value of k, then the closed loop pole move in this direction. Okay? Initially, if I do it in more details, so if this is, let's suppose, -3 and this is -4, so these are my plant poles. So initially they will move towards each other. How do I know that? I know because I know root locus. You will know that too once you study root locus. So I do not need to do any calculation. I know that initially they will move towards each other. And at certain point, they will collide with each other. Once they collide with each other, one of them will move upward and the other one will move downward. at 90 degree. ठीक है? यहाँ तक clear है student?
Yes, sir.
ठीक है? Now, looking at the root locus shows you the path of the closed loop control system. Path of the whole closed loop control. सिर्फ GFS की हम बात नहीं कर रहे, पूरे system की बात कर रहे हैं. So, root locus shows you the path of the closed loop control system poles as we increase the value of K. Looking at this path, can you see this path ever coming into the left-hand plane?
No, sir.
No, sir.
So what is the conclusion? I'm going to ask you a question, you will have to answer it. Would any value of K from 0 to infinity, would any value of K make the whole system, closed loop transfer function system, stable?
No, sir.
No.
Looking at the root locus. So your answer is no, which is the correct answer. Which is the correct answer. As you look at the root locus, you find out that no matter what value of K I use for this system, the system will not be stable. Okay? For some other system, let's suppose there is another system, which is, let's suppose, S plus 1. So we have a 0 in this case. Okay? We have two poles at -3 and -4, and we have a 0 at -1. Now, since I know root locus, now in this case, when we increase the value of K, because now this S plus 1 will come over here. K into S plus 1. Okay? So this will now become S squared minus 7S plus KS, or minus plus 12 plus K. This will be mine. Now the root locus for this system will be something like this. Okay? Initially, when K is small, the closed loop poles will be somewhere here. As K value increases, the closed loop poles will move towards each other and they will collide with each other. As K value further increases, the closed loop poles will start moving in this direction. Further increases in this direction. Further increases, further increases. For example, at K is equal to 10, the system, two poles, will move from the left-hand plane and will come onto the imaginary axis. For value of K value equal to 10, would the system be stable, unstable, or marginally stable then? Students?
It will be, sir, unstable.
नहीं, the whole system, plant तो unstable होगा, क्योंकि plant के poles तो ये जो हमारे पास plant है, sorry,
Sir, marginally stable होंगे, sir.
it will be marginally stable, क्योंकि जो पूरे system के poles हैं, वो अब imaginary axis पे आ गए, यहाँ से गायब हो गए, system के poles यहाँ पे नहीं अब, वो यहाँ पे, एक यहाँ पर, एक यहाँ पर है. So the system is marginally stable. If I increase K value to, let's suppose, 15, तो अब दो poles यहाँ से move करके यहाँ पे आ जाएंगे. अब system
Stable, sir.
it will be stable, or will it be underdamped? Underdamped, because the two poles of the whole system, पूरे system की हम बात, the two poles will be in the complex plane, left-hand side complex plane. If I further increase the value of K, these two poles may come and strike each other at this point on the real axis. Now the system has two real and repeating poles. Now the system has two real and repeating poles. Is this, now my question is the system stable, unstable, or marginally? Okay, good. It is a stable system. Is this stable? Is the system critically damped, underdamped, undamped, or overdamped system? Increase the value of K. One of the pole will move in this direction and the other pole will move in this direction. For
Stable, sir.
Stable.
is the system critically damped, undamped, overdamped, or is an overdamped system? Now do you see the power of a controller? Now do you see a power of a feedback control system?
Yes, sir.
Samajh student?
Yes, sir.
So we started with an unstable system. There was no way to make that unstable system without changing the system itself. Okay? You will have to change the physical system side. But if you are given an unstable system as a control engineer and you are asked to stabilize the system, you can do it by placing that unstable system in a feedback control system, and then using a controller. It can be a proportional controller, it can be a PD controller, proportional derivative controller, proportional integral controller, or a PID controller, or any other control. There are a lot of controllers in control system.
Sir,
So it can be any controller. Yes.
सर ये के किस चीज को शेयर कर रहा है सर? मेरा इंटरनेट डिस्कनेक्ट हो गया था सर, तो मैंने अभी ज्वाइन किया सर.
K represents the proportional gain. It basically, so whatever value of K, whatever value of error comes here, so this is E of S. The signal here is E of S. K basically multiply it with some value, constant value. So for example, K is equal to 10. If the signal value is, let's suppose, 0.1, then 0.1 multiplied 10 will make the signal equal to 1. Samjhari? So a proportional controller basically provide gain to the error signal. It either magnify or reduce the error signal. मेरे ख्याल में लिखमान फिर डिस्कनेक्ट हो, चलें वो रिकॉर्डिंग में देखेंगे. यहाँ तक
यस सर.
ठीक है, यहाँ तक क्लियर है स्टूडेंट्स?
Clear, sir.
सर के बेसिकली कंट्रोलर है.
K जो है प्रोपोर्शनल कंट्रोलर है. K is a proportional controller.
ओके सर.
ठीक है. PID, proportional integral derivative controller. PID is a amalgamate controller of three controllers: proportional, integral, and derivative control actions. Okay. Okay. Now, if you do not,
सर आप ये वीडियो अपलोड करेंगे लेक्चर के बाद या रिकॉर्डिंग जो है सर?
होगी. For one
ठीक है
week.
सर. थैंक यू सर.
Okay. So now that what other way we can tell whether this closed loops control system is stable or not depends on the value of the numerator of the feed forward part. Okay. So let's suppose you do not know root locus. हम imagine करते हैं कि आपको root locus का नहीं पता. ठीक है, or actually you do not know root locus. ये तो मैंने आपके सामने draw किया. Can you tell whether any value of K will make this system stable or this system stable? Any value of K, can you tell अच्छा, मैं आपसे क्वेश्चन पूछूंगा, ठीक है, and you answer me at least once, ठीक है. Question number 1. This, and I want to know that plant itself is unstable. I want to know that whether this whole system, including the plant and the feedback control loop, in the plant inside the feedback control loop. My question is, can you find out whether this system is stable or unstable? The whole system, feedback control system, not the plant itself. We know that the plant is unstable. My question is the whole feedback control system stable or unstable?
So it can be stable, it can be unstable depending on the K.
K value. Good. Is the right answer. Now, my question is, can you find the values of K for which the system is stable or unstable without, don't consider Lucas, we'll separate topic. What you have learned, can you find the value K for which the system is stable or for which the system is unstable?
No, sir.
You can actually, but you will have to do thousands of calculation. First, you put K is equal to 1 and solve this polynomial for roots. K की value 1 put करें ना, and then solve it. When you solve it, you will get some value of the closed loop poles. If the closed loop poles are in the right hand plane, then for that value of K, the system is unstable. Then what you do, you increase the value of K to, let's suppose, 2 or 1.1 or 1.01 or whatever. You keep on increasing the value of K and then calculating the roots. Then increase the value of K, then calculate, then increase the value of K, then calculate the root, then increase the value of K, then calculate the root. So here you may have to perform this calculations 10,000 times, 1,000 times, million times, billion times, whatever is your requirement.
So we can select any root and then find the K for it.
Yes, you can also do that, but you do not know the root location. आपको root locus path का तो आपको नहीं पता ना, ठीक है?
That's the problem.
ठीक है? Now that means that you can answer this question, that for K is equal to 5, for K is equal to 2, whether the system is stable or unstable. You can answer this question, because what you will do, you will find out the closed loop transfer function, and then you put the value of K in that denominator, and you find the roots of this denominator polynomial, and by looking at the roots, you can find out whether the system is stable or unstable for that value of K. But if I ask you, for what range of K the system is unstable, and for what value of K the system is marginally stable, then there is no practical way. Up till now, you have not studied any practical way to answer that question. You can answer that question either through raw stability criteria which we will study today, or through root locus. Okay? Even we may still use raw stability criteria. But anyway, for now, यहाँ तक clear है why we study raw stability criteria. Students?
Yes, sir.
Okay? For an unstable, for a plant system, we do not need raw stability criteria, because all we have to do is find the poles of the characteristic polynomial. For a closed loop system with variation, such as a proportional controller with a variable parameter such as K, we cannot find the closed loop poles location, or it is not feasible, or it takes huge amount of time to find closed loop parameters, closed loop poles location for a variable parameter in a closed loop feedback control system if the range is a large range. Okay? For that reason, we study raw stability criteria. Okay? So number of unstable poles, we can find the stability of a system using computer-aided analysis such as MATLAB. We can use raw stability criteria. We can use Nyquist stability criteria. We can use root locus stability criteria. In our course, we will study these two methods to study the stability of a closed loop feedback control system. So how does raw stability criteria works? It's not a complicated method. All you have to do is, if you have a system, let's suppose you have a system, let's do an example. Let's suppose you have this system, okay? You have this system. Is there any question about this system? It's basically a feedback control system. Okay? It's basically a feedback control system. So we have this is our, and in the feedback part, we have a KA, and we also have K theta here. Okay? Now, let's make it simple. Let's make it this problem. Okay, let's look at this problem. So we have a Planck transfer function, and we have a controller proportional controller with a proportional gain of K. Now, the question here is for because it has 3 poles, S is equal to 2. None of the poles is in the right hand plane. Therefore, plant is stable. Okay? Now, the question is the whole system stable? Is the whole closed loop negative feedback system stable? And for what value of Kp? Okay. So to answer this question is that the stability of this system is a function of Kp, as we looked in the previous slides. The value of Kp may make this system keep the system as stable. So how can we find the range of Kp? Question. For raw stability problems, you will get a question like this: what value of Kp what value of Kp will keep the system stable? This will be your question. This is your typical exam question. You're given variable parameter, in this case proportional controller gain kp, and you're asked the question that for what value of kp the whole system, सिर्फ उसकी बात नहीं कर रहे, we are not talking about the transfer function, we are talking about the whole system. For what value of kp will keep the system stable? Now kp can have any value from 0 to equal and less than infinity. ठीक है, यहाँ तक clear है student? Question? Students?
Yes.
Clear, sir.
Okay. Okay. Now step number one for this type of for raw stability problem, you will do basically 3 steps, and these are not some textbooks steps. This is for explanation purpose. So step number 1, find T of S, which is closed loop transfer function of the system. ठीक है? To make raw stability table. Three, interpret table for stability. That will be your answer. Okay. Step number 1, find the transfer function of the closed loop feedback control system. Step number 2, make a table, this table here. Step number 3, look at the table and from the table find the value of kp for which the system is stable. ये तीनों steps सबको याद होंगे? Will everyone remember this 3 steps? Step number 1, find the closed loop transfer function. Step number 2, make the raw stability table. Step number 3, interpret the raw stability table. Clear यहाँ तक students?
Yes, sir.
ठीक है? So now this we will consider it as our Cron transfer function. Then the closed loop transfer function, this पूरे loop का जो transfer function है, that will be equal to k g of s divided by 1 plus k g of s. Closed loop transfer function T of s. What is the characteristic equation of closed loop function? Into 1 divided by s into s plus 1 into s plus 2 divided by 1 plus kp divided by s into s plus 1 into s plus 2. That comes out to be k s plus 1 s into s plus 1 into s plus 2 divided by LCM ले लेते हैं, ठीक है? Here LCM, so it will be s into s plus 1 into s plus 2. That comes out to be s into s. ठीक है? ये दोनों कैंसिल हो जाएंगे, डिनोमिनेटर कैंसिल हो जाएंगे, and our closed loop transfer function will come out to be p over s plus kp. ठीक है? Clear यहाँ तक?
Yeah.
Okay. Now, our characteristic equation. What is the characteristic equation of closed loop transfer function? हमारे केस में, what is the characteristic equation of a closed loop transfer function? It is s into s plus 1 into s plus 2 plus kp. that comes out to be equal to 0. That comes out to be s into s squared plus 3s plus 2 plus kp equal to 0, or that comes out to be s cubed plus 3s squared plus 2s plus kp equal to 0. ठीक है, जो कि यहाँ पे लिखी हुई है, s cube plus 3s plus 2s plus kp. ठीक है, क्लियर है यहाँ तक स्टूडेंट्स?
Yes, sir.
So find the closed loop transfer function. You are telling first step should be find characteristic equation of closed loop transfer function. ठीक है? Characteristic equation of closed loop transfer function. So we just did step number 1. Step number 1 is to find the closed loop characteristic equation of a transfer function. Step number 2 is to make the Rouse stability table. Okay? For that, we'll come back here. Assume this is a closed loop characteristic polynomial. This is a closed loop transfer function characteristic polynomial. Then to make a table, let's do an example. Actually, let's do an example. Let's look at this example. I'm going to write let's add a page. Let's say we have S5 plus 3S4 plus 2S cube plus 1s square plus 6s plus 1. Let's suppose this is d of s characteristic polynomial of closed loop transfer function. ठीक है, जो अभी हमने थोड़ी देर पहले डिराइव की थी, अब जरा मैं इसके लिए मतलब ये इस a different characteristic polynomial क्योंकि I need a little bit higher order characteristic polynomial to explain how to come up with the Rouse stability table. So imagine if this is a characteristic polynomial of a closed loop transfer function, to draw the Rouse stability table, you will start with the highest power, S5. Then below it, you will write one lower power, S4. Then below it, you will write S3. Below it, you will write S2. Below it, you write S1, and of course, S0. यहाँ तक clear है? Is it clear up till now? Students? Any question?
Clear, sir.
Okay. Next, you will write the coefficients. So here the coefficient is 1. Next, the 4 coefficient will be written here. After that, so okay, let's start with first the odd coefficient. So the highest power is odd 5. So we write the first odd 1 coefficient, the second odd 2 coefficient, the third odd s raised to the power 1 coefficient, which is 6, and we will consider this as 0, which will be considered as even. Okay? Now, the first even is 3, the second even is 1, and the third even is also 1. Question, student? Students?
Sir, we are writing the coefficients or power of the
Coefficients. We are writing the coefficients. So, see, I'll repeat one more time. Let's make it 7. Let's make it 3. This is 6. Let's make it 5. Let's make it 9. Okay. So when you, in the raw stability table, the first two rows are filled with coefficients of characteristic polynomial of the closed loop transfer function. Clear है यहाँ तक? So starting with, so this is an odd row. In the odd row, the first coefficient is G.
सर ये एंड पे प्रोपोर्शनल जो के पी था वो लगाना पड़ेगा क्योंकि हम उसकी वैल्यू मालूम करना चाह रहे हैं.
अच्छा खैर बिल्कुल हम लगाएंगे जब हम वो प्रॉब्लम सॉल्व करेंगे we will use KP. For the sake of simplicity, I'm not using any variable in this raw stability table. ठीक है? Just for the sake of simplicity. Actual problem में probably you will have K value. Okay?
All right.
ठीक है? So, thank you for bringing it up. It's a good question. Okay. So I'll start with s raised to the power 5 coefficient, which is 9. Then I'll skip the even coefficient because the even power coefficient, this is the even power and this is the coefficient of the even power, will be used in the even row. So this is, since this is odd row, and this is even row. Why am I saying odd and even? Because this is odd and this is even. Now this row will only have odd power coefficients. So odd power is s raised to the power 4, s raised to the power 3, s raised to the power 1. So the power of these three terms is odd. And I'll write these coefficients. First coefficient, highest coefficient is 9. The second coefficient of s cubed, which is odd power, is 2. The third coefficient, which is of odd power, is 6. Clear यहाँ तक, student?
Yes, sir.
Now, s raised to the power 4 coefficient is 3. Now, since this is an even row because the first power is even, now the second even power is s raised to the power 2, even power term, and the third even power term is s raised to the power 0. We will treat 0 power as even. Okay? So 3, so first coefficient is 3, the second even power coefficient is 7, and the third even power coefficient is 5. Clear here, students?
Yes, sir.
Yes.
Okay. Now, coming back to that slide, where is this? Now, you know, highest power, second highest power. And then how do you fill the first row and the second row? You fill the first and second row from the closed loop characteristic polynomial itself. All the other entries in the table are done through calculations from the first two rows and the subsequent rows. So if I want to find this term, in our example, if I want to find this value, okay, what will I do? I'll take a determinant of these two, okay? I'll take a determinant of these two minus determinant of these two and divide by this value. So what I'll do here, I'll take a determinant of these two with negative sign. So let me do it clearly here. Minus determinant of 9, 2, 3, 7 divide by this value. If you take determinant of this, you will use this value. Okay? You will use this value and then you solve it. So when you solve it, it will become 9 sevens are 63 minus 2 3s are 6 divided by 3, that comes out to be minus 57 G.
Minus 19, sir. 19.
Minus 19. Thank you. Thank you for the help. So this will be so this will be minus 19. How would you do the second one? For the second one, we will take determinant of, for this one, we will take determinant of this and this. So this will be minus 2, this will be 6 and 5. So my next value will be minus 45 minus 18 divided by 3, which will be equal, क्या value आएगी? Students?
9 sir.
9 आ रही है?
Yes sir.
So this will be minus 9. Now assume that there was some other value. Let's suppose there was x and y. Then you will also calculate this value. Okay? And this value will then be x, y divided by 3. So this will be then becomes 9y minus 3x divided by 3, whatever value वो आप यहाँ पे put करें. Clear यहाँ तक students? Since we do not have any other values in this table, so you can treat it like this. So to find this value, you will have to use this column, which doesn't exist, so we can place 0, 0, and this will become 0 divided by 3 is equal to 0. So you can simply write 0 or write nothing. That is fine. Clear यहाँ तक students?
Yes sir, clear.
Yes.
Okay. Now let's go to the next row. For this one, we will take determinant of this and this. So this will now become 3 minus 19, 7 minus 9, and minus 19. Okay? That will come out to be minus 27 and plus 7 multiply 19. Divide by, anyone has a calculator?
Sir, 5.57.
Plus 5.57. Okay, for this value calculation, we will use 319 and 5 and 0. So 0 plus 5 multiply 19. So that will be 5. Answer will be 5. ठीक है ना?
Yes sir.
ठीक है? Okay. What will be this value now? अब आपने खुद मुझे students. Somebody? ये value क्या होगी? यहाँ पे क्या लिखूं? Minus 19, 5.5 minus 9, 5 divided by 5.5 will be equal to minus 19 multiply 5 plus 9 multiply 5.5 divided by 5.5. ठीक है? इससे क्या वैल्यू आ रही है? Any student? Students?
Sir, 8.27.
8.27. For this next value, we will use this one and this one,
0.
which will be 0. And for the last one,
It will be 5.
it will be 5, but let me write it. It will be 5.5, 5, 8.27, and 0, and 8.27. So 8.27 minus 0 multiply 5 into 8.27. So 8.27 और 8.27 जो है कैंसिल हो जाएंगे और यहाँ पर मेरे पास सिर्फ -5 है, -5. ठीक है. This is your part 2. This is your part 2. Now we have part 1 was to get the characteristic equation of a closed loop transfer function. Part 2 is to find or to calculate the Rao stability table. This is called Rao-Hurwitz or Rao stability table. This is part 2. Now part 3, so this is part 1, part 2, and now part 3 is interpret Rao stability table. इसे इंटरप्रेट करना. पहले दो स्टेप्स क्लियर हैं स्टूडेंट्स?
Yes, sir.
सर ये एस क्यूब तक 3 डिजिट्स आए हैं, -19, -9, 0, फिर 5.5 और 5 है, फिर 8.20. तो उसमें सर थर्ड डिजिट नहीं होगा?
अगर कैलकुलेशन मैंने आपके सामने की है, अगर कैलकुलेशन मतलब आपको ओके, हाउ शुड आई आंसर दैट क्वेश्चन? देखिए जरूरी नहीं है, जो मैंने आपके सामने फार्मूला लिखा है ग्रेजुअली आपके न्यू कम होते जाएंगे नंबर्स. As long as you follow this formula, don't worry about if there is no element here. You can write 0, 0, 0, 0. You can write 0, 0, or if you don't write 0, it is understood कि यहाँ पे 0.
ओके सर.
ठीक है? Because we are not interested in these values. You will see now. Now, if there is no additional question, I'll go to the third part of the Rao stability table, which is to interpret the table. Now, interpretation of the table is very interesting. We don't of values, not this one. Not S4, SQ, just the first column of values of the table. And we are now, I want you to find out the number of sign changes in the first column. So start with first number, it is +9. From +9 to +3, is there any sign change? Did sign change happen?
No, sir.
3 to -19, we have one sign change. I move from there to sign changes. Clear?
Yes, sir.
Yes.
If I move from 5.5 to 8.27, no sign change because both are positive. If I move from 8.27 to -5, there is another sign change. So 3 sign changes. Question, how many sign changes are there in the first column of the Rao stability table values? 3 sign changes. Now I'm going to answer your stability question. The stability of a system, whether it's a plant transfer function or a closed loop feedback control system transfer function, depends on number of poles in the right hand plane. Even if there is one pole in the right hand plane, the whole system is unstable. If this is the system closed loop system transfer function, this characteristic equation है. This characteristic equation की degree क्या है? What is the degree of this characteristic equation? Characteristic polynomial.
5.
5. So how many poles will this closed loop transfer function have?
5 poles.
5 poles. Now I can tell you that out of these 5 poles, 3 are unstable. Means 3 of the poles are in the right-hand plane.
Okay.
Okay?
Yes.
I'm
sir.
clear? I'm clear. Step number 1, find the characteristic polynomial of a closed loop transfer function. 3, interpret the Rouse stability table. How do you interpret the Rouse stability table? You look at the first column of the Rouse stability table values and find out the number of sign changes in that column. The number of sign changes are equal to number of unstable poles of that characteristic or unstable roots of that characteristic polynomial from which we calculated our Rouse stability table. Clear hai yahan tak, student?
Yes, sir.
Clear, sir.
Any question? Should I move forward? Let's solve that problem now.
Yes, sir.
ठीक है? So, coming back to the problem, that was, so I can start with a insert new slide. ठीक है? So, step number 1, our characteristic polynomial is d of s closed loop is s cubed plus 3s plus 2s 3s squared plus 2s plus k. That was our step number 1. Again, let's call it step number 1. Now we will draw the, we will find out, or we will calculate or draw the table for the, calculate the table, tabular values of Rouse stability table. And how do we do it? We start with the highest power, in this case is s cubed, then the next power will be s squared, then the next power will be s1, and the next power will be equal to s0. Then we fill the first 2 rows of a Rouse stability table from the closed loop characteristic polynomial. So starting s odd polynomial term, which is s highest odd polynomial term, which is s cubed, and its coefficient is of course 1. The next odd polynomial power term coefficient is 2. And since this is s raised to the power 0, so this is not an odd term, this ks raised to the power 0. So we'll move to the even polynomial. So the highest even polynomial term coefficient is 3. And the next even polynomial coefficient term is kp. Actually, this is kp. Okay. Did we miss anything?
It's okay.
Yeah, it's the same. Okay, so it's a very simple problem. Now we have to fill this table. So this value can be calculated as minus 132 kp divided by
3.
2. That comes out to be minus kp minus 6 or by 3, 6 minus kp divided by 3. Doesn't matter, चाहे आप ये लिखते हैं या ये लिखते हैं, एक ही चीज है, ठीक है? So I'll write 6 minus kp equal to divided by 3. So what will be the next term? This will be this column
0.
0, 0. So this will be 0, or I shouldn't write. I don't need to write anything. I can write 0, or I don't need to write anything. It's up to you. Okay? For the next case, our determinant value will be minus 3, 6 minus kp divided by
0.
3, and kp and 0 divided by 6 minus Kp divided by 3. So this comes out to be minus Kp into 6 minus Kp divided by 3 divided by 6 minus Kp divided by 3. ये दोनों कैंसिल हो जाएंगे, माइनस माइनस पॉजिटिव हो जाएगा, सो इट विल बी Kp. ठीक है. Part 2 of raw stability table. Step 2 of raw stability table or raw stability analysis. ठीक है. Next, let's interpret step 3 of the raw stability table. ठीक है. Now, of course, in the previous case, we didn't have any variable. In this case, we have 2 of the 4 values in the first column have a variable. But we are not interested in the actual value. What we are interested, we know that this is positive, that this is positive. If this is positive and this is also positive, then there will be 0 sign changes. Then if there are 0 sign changes, then there will be 0 poles in right hand plane. If there are 0 poles in the right hand plane, then the system will be
stable.
Will be stable. Now we have to make sure, if we want to keep this value positive, then, or start with simple one. If we want to keep this value positive, then Kp should be greater than 0.
And less than 6.
And very good. Similarly, we have to, if we want to keep this value positive, then 6 minus Kp divided by 3 should be greater than 0, which comes out to be, when you solve it, which comes out to be Kp should be less than 6. So answer to the question was, for what value of Kp the system is stable? The answer to that question is, the system is stable for Kp value greater than 0 to
6.
Less than 6. Clear?
Clear, sir.
Yes.
आसान है ना? Raw stability table is a very
सर ये
जी
Kp की वैल्यू सर ये इक्वल टू 6 भी ले सकते हैं ना सर?
नहीं, इक्वल टू 6 नहीं,
जरूरत नहीं है सर कि ये लेस देन 6 ले ले सर, क्योंकि वो भी तो 0 आ जाएगा सर, साइन चेंज तो नहीं होगा उसको.
साइन चेंज नहीं होगा, लेकिन हम बेसिकली पॉजिटिव रखना चाहते हैं ना, तो टिपिकली 0 की एक और इंटरप्रिटेशन है, उसमें अभी हम नहीं जाते. We will use Kp value of greater.
ओके सर.
ठीक है, पॉजिटिव.
सर 0 का साइन नहीं है, मतलब
ठीक है सर.
हाँ, 0 का साइन नहीं है, पॉजिटिव हम रखना चाहते हैं. ठीक है.
Yes, sir.
Okay, now this problem. Okay, and I'll quickly go over the slide. First, you will combine these 3 together. Okay, when you combine these 3 together, we get this value. Then you can move from one of the, this is a summation junction. So if you move K theta from one of the input to the summation junction to the output of the summation junction, यहाँ पे ले आए, then you will place an inverse 1 over K theta on all the other inputs to the summation junction. This inverse will cancel out this, and we will end up with K theta up here. ठीक है, ये ब्लॉक डायग्राम रिडक्शन है, चैप्टर 5. ठीक है. practice it. So from this diagram, you end up with this diagram. Okay. Now it's a standard feedback control system, and this is the closed loop. This is the transfer function T of S of this system. From this transfer function T of S, we find out the characteristic polynomial of closed loop transfer function. From the characteristic polynomial of the closed loop transfer function, we calculate or we fill the Rouse stability table. Okay? Once we have the Rouse stability table, the last part is to interpret this table. And in this table, as you can see, the first value, assume tau is a constant which is positive value. So if it is tau is positive, ये question में होना चाहिए. Plus 1 is positive. So if we don't want any instability, then this value should also be positive. So the product of Kp, if Kp, K theta, and K should be greater than 0 or should be positive. Since we are already given that K theta in the question, this is a book question or somewhere, K theta and K are already given as positive. So given a T, K, and K theta are all positive. Find value of Kp that makes system, closed loop feedback control system positive. Stable. Okay? So since these two values are already positive, if we want the whole product to be positive, then Kp should also be positive. That means Kp should be greater than 0, and then there will be no sign change and the system will remain stable. So this particular system is stable for Kp value, any value greater than 0, while this system is stable for Kp value range between 0 and 6 exclusively. ठीक है? Clear है यहाँ तक student?
Yes, sir.
अच्छा.
Yes.
अच्छा. अब यहाँ पे there is one issue. There is a issue here. Okay. There are two special cases for Rouse stability table or Rouse stability analysis. देखिए, Rouse stability analysis का एक और advantage भी है. For example, इस example में देखें, there is no variable, there is no k here. But still, using Rouse stability table is advantageous in a way that, for example, if you have fifth degree polynomial, finding the 5 roots of this fifth degree polynomial is not easy task. It's a time consuming task. But if you're not interested in the exact value of the roots of this fifth degree polynomial, you are only interested if any of the root is in the right hand plane or not, then you can use, rather than finding the roots of the polynomial, roots numerical value of the polynomial, you can use Rouse stability calculation, which are relatively easy to perform, and you can find out whether this polynomial has any root which is in the right hand plane or not. ठीक है? समझ आ रही है इस बात की? Students?
Yes.
ठीक है? What I'm saying, that Rouse stability table is very useful if you have if you have some parameter like k or alpha or tau, some variable in the characteristic polynomial of a closed loop transfer function. You probably have very few options to find out the system, whether the system is stable or not. But if there is no variable like k, like in this case, all the values are numerical constant, all the coefficients are numerical constants. In this case, you can either use raw stability table or raw stability criteria, or you can solve this polynomial for the roots of the polynomial. You can find out whether the system is stable or not, either using raw stability criteria or finding the roots of this characteristic polynomial numerically. Both of the method will give you an answer that you can interpret into whether this system is stable or not. But finding a 5th degree polynomial roots is time-consuming, tedious work, or 7th degree or 10th degree polynomial roots are time-consuming, tedious work. Relatively, at least I feel that calculating the raw stability table is relatively easier and simpler method. So if you are not interested in actual roots value, but only interested to figure out whether the roots are in the right-hand plane or not, you should use the raw stability criteria, stability analysis, rather than calculating the roots. That's what I wanted to say. Next, there are two special cases of raw stability criteria. There are two special cases of raw stability criteria. Case number one. Case number one comes, we need case number one is because all the time in all our calculation, this element is denominator. This element, or in the next calculation when we are calculating some other term, then this will be denominator. Like we always have a denominator. Imagine if there is a 0 here. If there is a 0 here, this will become 0, and this whole term will become infinity. If you end up with only one infinity, then the rest of the table will all become infinity. And this will be useless. You will not be able to use the raw stability table for stability interpretation or stability analysis. Yahan tak clear, student?
Yes, sir.
So how do we deal with this kind of situation? If we end up with a 0 anywhere in the first column, here, anywhere, if there is a 0, rather than writing 0 in the first column, not anywhere else. Anywhere else, if there is a 0, it's fine, no problem. But only on the first column, because the first column values eventually become denominator for calculation of the next value. So if you end up with a 0, let's suppose this becomes 0, you do not write 0 here, you write epsilon, where epsilon is a very small quantity approaching to 0, okay? Very small positive quantity approaching to 0, okay? समझ आ रही स्टूडेंट यहाँ पे बल्कि लिखा हुआ. So epsilon is a positive constant, a very small positive constant for all intent and purposes, okay? So it's a very small positive constant. Imagine that epsilon is 0.00000000001 million zeros and 1. Okay? But it is a positive constant, not a negative 0.000001. It is a positive 0.00000. A very small quantity which approaches to 0, a very small positive quantity which approaches to 0. Okay? Now let's say in this problem, if we try to solve this problem, we start with S5, S4, S3, S2, S1, and S0, and then we will put the odd powers here. 1, 5, 12, and the even powers in the second row, 1, 5, and 10. Okay? Next, we have to perform our calculation. For this term becomes, for this term, it is minus 1155 divided by 1. That comes out to be minus 5 minus 5 divided by 1 is equal to 0 divided by 1 is equal to 0. So Initially, it comes out to be 0, but I'm not going to write 0. Rather, I'm going to write epsilon and note here that epsilon is a small positive constant approaching to 0. Okay? Now, once you write epsilon, you will perform all the subsequent. Okay, after that, we calculate this. Okay? Now, when we try to calculate the next value, we will have to deal with epsilon. So if I want to calculate this value, this will be equal to 1, 5, and epsilon 2. This is minus, and this is epsilon. So this becomes minus 2 into minus 5 epsilon divided by epsilon. So this becomes minus 2 by epsilon plus 5. ठीक है? अच्छा, अगर आप देखें स्लाइड में there is only minus 2 by 5. Where does epsilon goes? This is because they have treated it like this. So minus 2 divided by minus 2 plus 5 multiply, let's suppose 0.0000000000000 infinite 0 and 1. What will be this practical value of this 5?
Approach to 0.
Approach to 0. So epsilon divided by epsilon will be, so we end up with minus 2 by infinity, 2 by epsilon. Okay? And then we calculate the next value. This next value will be calculated as 10 will be calculated as between this and this. So this will be 10 and 0, and this comes out to be 10. So this is our next value, 10. Similarly, when we calculate this next value, it will be between this and this column, which will be epsilon divided by minus 2 by epsilon into 2 and 10 minus divided by minus 2 by epsilon. That comes out to be minus 10 epsilon, okay, 10 epsilon, and plus 4 by epsilon, okay. Now again we will use the same logic, divide by minus 2 by epsilon, okay. Cancel. We will assume that this approaches to 0. Since epsilon is a very small quantity, multiplied any quantity will approach to 0. So we'll end up by 4 by epsilon divided by 2 by epsilon. So epsilon cancel, and we'll end up with 2. So our next value is 2. And similarly, we calculate 10. Once we have all these values, then our table is complete. Part 1, find a closed loop characteristic polynomial, which was given to us in this example. Part 2, probability table. Part 3, interpret the Rouse stability table. Now, if we see this is positive, we assume epsilon to be a positive small quantity. So this is positive. Now this is minus 2 divided by positive quantity. Whatever this value, the sign, we know that epsilon is a positive quantity. That's what we assume it to be, a positive constant. Since it's a positive quantity, that means that whatever the magnitude, this whole value is negative, because minus 2 divided by positive value will be a negative value. And then 2 is positive and 10 is positive. Therefore, in this whole system, there is one sign change from here to here, and a second sign change from here to here. So there, in this system, which has 5 closed loop poles, out of the 5 closed loop poles, since there are two sign changes, therefore out of the 5 closed loop poles, two poles are unstable.
In the right hand.
Or in the right hand plane, or two poles are unstable. There, yahan tak. So first of all, we discussed the background. Why do we need Rao stability table? We discussed that you can find the stability of a plant transfer function, but if you place the same plant in a closed loop feedback control system, and there is any variable in that closed loop feedback control system, such as proportional gain K, then because of that variable, this closed loop feedback control system will have infinite values. For any values of K, the closed loop transfer function pose will have different location on the complex plane. So it is not easy to find out the range of K for which the closed loop control system will be stable, unstable, or marginally stable. To solve this problem, to tackle this problem, we have multiple ways to find the range of a variable for which the closed loop system will remain constant. One of them is Rao stability table. In a Rao stability or Rao stability analysis method, we perform the analysis in 3 steps. Step number 1, we find the closed loop transfer function characteristic polynomial. Step number 2, we come up with the Rao stability table. We fill the table, first 2 rows of the table from the characteristic polynomial closed loop, and calculate the rest of the rows of the table as per Rao stability analysis calculation method. And once we have the Rao stability table, part 3 of the Rao stability analysis is to interpret the first column of values of the Rao stability table to look for the sign changes. Based on the sign changes, we can either tell how many poles are in the right-hand plane or unstable poles, or we can tell for what value of K or Kp, for what variable in the closed loop transfer function value, the system will remain stable. Clear?
Yes.
So clear.
Okay. Now there are 2 special cases of Rao stability criteria. Case number 1, when you end up with a 0 in the first column of a Rao stability table values. Okay? We treat, this is case 1. Any, चाहे एक दफा है, चाहे 2 दफा है, चाहे 1000 दफा है, doesn't matter.
Excuse me, sir.
जी.
सर ये इधर सर नेट का मसला है सर, तो अगर अटेंडेंस ले ले तो सही हो जाएगा सर। इधर ये नेट बार बार डिस्कनेक्ट होती है तो उससे क्या सर।
ठीक है। अच्छा, मैं इस वक्त अटेंडेंस नहीं ले सकता, कुछ इशू है, मुझे मीटिंग से बाहर जाना पड़ेगा, दोबारा आना पड़ेगा, तो थोड़ा सा खैर गुजारा
सर अभी कितना रहता है सर?
10 मिनट तकरीबन, ज्यादा 15 मिनट से ज्यादा नहीं है। एक और लास्ट केस है, देन वी आर डन, वन मोर केस, ठीक है? सो बेयर विद मी,
ले लेते हैं ना सर, बहुत ज्यादा हो गया है आज के लिए, प्लीज सर।
नहीं ये टॉपिक आज खत्म करना है जी
सर, ये खत्म कर दे आज।
हाँ, ये खत्म करते हैं, ये फिर हम दोबारा नहीं कर सकते। अगर कल मुझे रिपीट करना पड़ेगा तो फिर मेरा आधा घंटा 1 घंटा जाया होगा, ठीक है? और हमारे पास टाइम बहुत कम है, वी हैव टू, आप सबको टाइम टेबल मिल चुका है, तो हमारे पास टाइम नहीं है इतना। ओके, आई विल गो बैक टू द स्लाइड। केस 2, rather than case 2 arises that rather than single 0, the whole row during calculation, the whole row comes out to be 0. Students?
Yes,
समझ आ रही है? कि पहले केस में क्या था कि हमने we use these two columns to calculate this value. It was non-zero. Okay? Then this value was calculated using these two columns. This is again non-zero. But when we use these two columns to calculate this value, that comes out to be 0. Okay, हमने कहा no problem. That's not a problem because we know in case 1 that all you have to do is to replace this 0 with a positive small constant epsilon which approaches to 0. Okay. Next, we try to calculate this value from this column and this column, but this also comes out to be 0. Now, if both of these values comes out to be 0, and if you use epsilon, still this will not work. You will get, this will not be the proper way. If you have the whole row to be 0, you have to replace it with a determinant or with a derivative of this row. So this whole row becomes 0, 0. This is case 2. Now I cannot write 0, 0 here. What I'll do is I'll take this row. This row is, I can write it in terms of polynomial. The 3 is a coefficient of s squared, and 12 plus 12 is a coefficient of next, since this is an even row, so the next coefficient will be s0. So I'll take this polynomial, let's call it a of s, okay, and I'll differentiate it with respect to s. When I differentiate it with respect to s, it comes out to be 6s plus 0. Now, rather than writing 0, 0, I will write 6 and 0. 6 and 0. 6 is a coefficient of s, 6 is a coefficient of s, and 0 is a coefficient, it doesn't exist. समझ आ रही इस बात? Otherwise, मैं आपके लिए एक नया slide करता हूँ. Let's suppose we have this thing S5, S4, S3, S2, S1, S0. So S5, let's suppose it is 2, 3, 4, 5, 9, 7. Let's suppose this whole row comes out to be 0, 0, 0. Okay? When I calculate my values, imagine when I calculate all these three values as per raw stability calculation, table calculation, this whole row of S cube comes out to be 0, 0, 0. Okay? If it comes out to be 0, you cannot write epsilon here and keep these two values as 0, 0. That will be wrong. Okay? What you will have to do is that rather than writing 0, 0, you will take the upper polynomial. Now the upper polynomial, you can convert it into polynomial, the upper row into polynomial. The 5 is a coefficient of S4, we know that. Okay? 9th is a coefficient of next even polynomial. And S square. And 7 is a coefficient of next even polynomial, which is s raised to the power 0. So you can come up with any polynomial a of s, write it p of s, okay? And then differentiate this polynomial with respect to s. Now, if you differentiate this polynomial with respect to s, you will get 20s cubed plus 18s plus 0. Okay? So the next, now, s cubed term is 20. The next coefficient here will be s raised to the power 1 because it's an odd row. Okay? So this will be 18. The next quotient here is nothing. So you don't write anything. Okay? And then you solve for the rest of, so the next value will be calculated using this value. 5, 20, 9, 18, minus, divide by 20, it will give you some value. The next value, this will be calculated between this row and this, and it will give you some value. And you will complete the whole table. समझ आ रही?
Yes, sir.
Is it clear? ठीक है? Now, now, once you know how to deal with a raw stability table condition where the whole entire row is equal to 0, this is how you deal with it. The second part is, what is the meaning of entire zero row? अगर सिंगल एक जीरो आ जाता है वो बस कैलकुलेशन की वजह से आ जाता है, उसको हम मतलब एक जीरो आ जाए और यहाँ पर कुछ values आ जाए, तो that means it has no other significance. It has no other significance. It means that by chance those values were such that their determinant as per this formula was 0. And all you don't have to think about any interpretation of that. All you have to do is replace 0 with an epsilon. That's it. But if you have a entire zero that you replace entire zero, then there are two steps to this. Number one is how to calculate the table. For calculation of the table, how to proceed with the tables, you perform this procedure, which becomes 20 and 18, and you proceed with the calculation. That is the procedural part of the entire zero row in raw stability table. The second part is interpretation of an entire zero row in the raw stability table. The interpretation of a entire zero row means that if you end up with a 0, 0, this means that this polynomial, which is 55s4 plus 9s squared plus 7s raised to the power 0. This polynomial is a factor of the original polynomial, which was 2s5 plus 5s4 plus 3s cubed plus 9s squared plus 4s plus 7. ठीक है? This was our original polynomial, d of s. This means that this is a factor of this polynomial. This means that this polynomial, d of s, can be written as 5s4 plus 9s squared plus 7s0 multiply some other factor, remaining factor. समझ आ रही इस बात की?
Yes, sir.
Yes.
ठीक है? Now, if you have that means that you have an even polynomial factor, and there are implications for that which are here. Yes, slide. If you have a even polynomial, pure even polynomial. Again, if you have a pure even polynomial factor, it's a factor, but it is pure even polynomial. There is no odd power terms in this factor. If that is the case, then the roots, then you need to know about the roots of even polynomial. What is an even polynomial? Even polynomial is a polynomial who has only even power terms in the polynomial. ठीक है? And even polynomial roots follow these three rules. The roots are symmetric and real. The roots are either symmetric and real. The roots are symmetrical and real. The roots are symmetrical and imaginary. The roots are quadrilateral. ठीक है? अच्छा In other words, let's suppose I have an even polynomial like this. Let's suppose it is y squared, sorry, s squared plus 2 is equal to, this is my, let's suppose, even polynomial, p of s. Now, if you look at the roots of this p of s, if I make it equal to 0, then I have s is equal to plus minus under root 2 iota. Okay? That means that one of the root is at plus 2 iota and the other root is at minus 2 iota. If you see that the two roots are mirror image across the origin, they are mirror image across the origin. Okay? In simple words, if you ever have an even polynomial, the even polynomial will always be a mirror image. All the roots of the polynomial will have their mirror image across the polynomial. For example, if I have an even polynomial and one of the root is here, then its mirror image is here. Then the second root should be here. If one of the root is here, then the second root should be here. If one of the root is here, then the mirror of this is here. If one of the root is here, then the mirror of this is here. इस बात की समझ आ रही है? Let me summarize it. If you have a pure even polynomial, then the roots of that pure even polynomial will follow the restriction that all the roots of the pure even polynomial will be mirror image of each other. Mirror image of each other. वो mirror image होंगे एक दूसरे के. इसके अलावा और वो नहीं हो सकते. For example, if I have a even polynomial with two roots, if I have one root here, then the other root need to be here. ठीक है? If I have mirror two, let's suppose one here, then the other root should be here. If I have a one root here, then the mirror image of this need to be here. ठीक है? Now again, a complex.
टाइम बहुत हो गया सर.
हाँ?
पर टाइम सर.
अच्छा. Similarly, this root cannot exist in the complex plane without conjugate. So it need to have a root here. Then if this root exists here, then there need to be a mirror image here. So and that's finished the lecture. ठीक है? जो मैं अटेंडेंस ले लूँगा, इसके बाद जो स्टूडेंट जो है इंटरेस्टेड हैं वो डिस्कशन के लिए रह सकते हैं. जो स्टूडेंट जाना चाहते हैं.
अटेंडेंस ले ले सर, इशू बहुत आ रहा है सर.
अच्छा, क्या इशू है? What is the issue?
सर नेट मसला है सर, बार बार डिस्कनेक्ट.
अच्छा चलो ठीक है, मैं रिकॉर्डिंग स्टॉप करके I'll go out and come back.
मुनीब,
ये नेट का किस तरह मसला है यार ओवैस, ये यूनिवर्सिटी में कौन सा नेट का मसला गया? तुम तो
यार नेट तो खराब है ना, बार बार वो
वाईफाई यूज करते हो यूनिवर्सिटी का.
नहीं खराब है ना, अभी मसला आ रहा है.
सर वो
बिल्कुल मसला नहीं.
वाईफाई तो ना
हमारा मसला है तो पढ़ने
شور مكوي ظالمان وشور مكوي.
دروغ وإيمان.
ده لقمان نه ده لقمان سم دې په بس نه کوي.
كم جگہ مسئلہ نہیں ہے. तो गप څنګه لګي بیا دا गप څنګه لګي
सर प्रेजेंट यार सर्च करे
چې کلاس نه افلاین ولاړ شو کنه.
لکه سرچ ته جب شي
یله کاغه سر دونه په شوق باندې دا چرته یو ټیچر دی کنه زمونږه چې لغون ته په خونه او لغون ته په خپل انټرست باندې سبق کوي، نور ټول ځان خلاصي او ته دې نه پرې دی.
حسن भाई सर ऑनलाइन दे
सॉरी
खलील आप भी कुछ कर लो यार।
हेलो स्टूडेंट्स।
यस सर।
अच्छा,
जी
मैंने
सर।
आपकी अटेंडेंस ले ली है। जो स्टूडेंट जाना चाहते हैं वो जा सकते हैं, ठीक है। और जो डिस्कशन फर्दर डिस्कशन करना चाहते हैं तो उनके लिए मैं अवेलेबल हूँ। वी कैन डिस्कस द स्लाइड फर्दर, ठीक है। बाकी हो आपका कंप्लीट हो गया लेक्चर, आपका आज का कंप्लीट। ठीक है। सो डू यू हैव एनी क्वेश्चन? क्योंकि ये थोड़ा सा दिस पर्टिकुलर कॉन्सेप्ट जो ये थोड़ा सा गंभीर है, थोड़ा सा मामूली सा। सो लेट मी आस्क यू कि आप लोग जो है कहाँ पे आपको समझ नहीं आई, ताकि मैं उसको एक्सप्लेन कर सकूं। स्टूडेंट्स,
ये कॉन्सेप्ट उस के साथ रिलेटेड है जब रो जीरो हो जाती है।
किस चीज के साथ रिलेटेड है? हाँ, ये उसी की हम बात कर रहे हैं ना। हम ये बात कर रहे हैं, हम ये कह रहे हैं कि जब रो जीरो हो जाता है ना, तो रो आपके पास ऑलमोस्ट ऑलवेज रो जो है वो ऑड पॉलिनोमियल में आपके पास जीरो होगा। देखिए इस एग्जांपल में देखें, ठीक है। अच्छा, वैसे इवन पॉलिनोमियल में भी जीरो हो सकता है। आई विल कम टू दैट। वो एक इंटरेस्टिंग एक दूसरी देखें। अगर आप देखें ये ऑड पॉलिनोमियल जीरो हो गया, तो इसका मतलब ये है कि अगर ऑड पॉलिनोमियल जीरो हो गया तो इसका मतलब कि इससे ऊपर वाला जो इवन पॉलिनोमियल है वो परफेक्ट फैक्टर है इस पॉलिनोमियल का। तो आप डायरेक्टली कह सकते हैं, यानी ये नीचे रो जीरो हो गई है ना, ये वाली रो, तो आप कह सकते हैं कि ये वाला पॉलिनोमियल जिसको हम लिख सकते हैं एज p ऑफ 3s² प्लस 12, हम कह सकते हैं कि ये 3s² प्लस 10 जो है ये इस d ऑफ s को एग्जैक्टली डिवाइड करता है, क्योंकि ये इसका फैक्टर है। इसकी समझ आ रही है स्टूडेंट्स?
यस सर।
यस
ठीक है। अब अगर ये इसका फैक्टर है, फॉर एग्जांपल देखें हमारे पास क्या होता है। देखें अगर मेरे पास ये है s+1 और s+2, ये अगर मेरे पास d ऑफ s ये आ जाए मिसाल के तौर पे, एक मिनट, अगर मेरे पास d ऑफ s की वैल्यू ये आ जाए s+1 एंड s+2, मिसाल के तौर पे ये आ जाए, तो मैं ये कह सकता हूं ना कि s+1 जो है ये g ऑफ s का फैक्टर है। ट्रू है ना? इसमें ये तो बिल्कुल बेसिक बात है ना, परफेक्टली डिवाइड करता है, फुल डिवीजन करता है, ठीक है। सो इसका मतलब है कि मैं फॉर एग्जांपल अगर यहाँ पर बहुत कुछ और भी लिखा हो, फॉर एग्जांपल यहाँ पे ये लिखा हो s² प्लस 2s प्लस या s³ प्लस 2s² प्लस 3s प्लस 4, अगर ये भी लिखा हो, तो मैं ये कह सकता हूं कि ये जो पोलिनोमियल है इसका एक रूट जो है वो -1 है। कैन आई से दैट?
यस सर।
ठीक है ना? तो अगर मैं ये कहूं कि ये जो इसी सेंस में, इफ इन द सेम सेंस आई से कि ये वाला जो पोलिनोमियल है, दिस पोलिनोमियल which is 3s² plus 12, this polynomial, if I know that this polynomial is a factor of this, larger polynomial, रूट्स होंगे, इसके जो रूट्स होंगे, इस फैक्टर के जो रूट्स होंगे वो इस पोलिनोमियल के भी रूट्स होंगे।
यस सर।
ठीक है, अब
बिल्कुल सर।
यहां तक आप समझें, फिर हम आगे जाते हैं। ठीक है, अब हम आगे जाते हैं। अब हम आते हैं कि ये जो भी हमने डिस्कस किया इसका कंट्रोल के साथ कोई ताल्लुक नहीं है, ये तो फैक्टर्स के साथ ताल्लुक है, रूट के साथ इसका ताल्लुक। ठीक है, अब हम अब उसमें आते हैं। अब अलजबरा की एक और बात मैं आपको समझा दूं, अलजबरा की एक और बात समझा दूं। अलजबरा की एक और बात ये कि जब आपके पास प्योर पॉलिनोमियल हो, प्योर इवन पॉलिनोमियल हो, प्योर इवन पॉलिनोमियल से मिसाल क्या है? फॉर एग्जांपल अगर मैं लिख लूं s4 प्लस 2s प्लस s स्क्वायर प्लस s प्लस 7, क्या ये प्योर इवन पॉलिनोमियल है?
नो सर।
स्टूडेंट, क्यों?
सर क्योंकि
s पावर 1 जो है वो तो ऑड टर्म है ना, ऑड पावर टर्म है, मतलब ये तमाम पावर्स जो है इवन पावर्स नहीं है। सो दिस इज नॉट अ प्योर इवन पॉलिनोमियल। ठीक है, लेकिन अगर ये टर्म खत्म हो जाए, अब इज दिस अ प्योर इवन पॉलिनोमियल?
यस सर।
सारे पावर्स इवन है सर।
ठीक है, क्योंकि बिकॉज ऑल द टर्म्स इन दिस पॉलिनोमियल हैव इवन पावर्स, 0 2 4 6 8 कुछ इस तरह की पावर्स। ठीक है, now if you have even polynomial, pure even polynomial, तो इसके जो रूट्स हैं it will always, इसके जो रूट्स होंगे it will always be mirror image of each other, ये हमेशा एक दूसरे के मिरर इमेज होंगे, इसके अलावा और कोई पॉसिबिलिटी है ही नहीं। समझ आ रही इस बात की?
यस सर।
तो फॉर एग्जांपल अब ये 4 डिग्री पॉलिनोमियल है ना, दिस इज अ 4 डिग्री पॉलिनोमियल। सो 4 डिग्री पॉलिनोमियल के कितने रूट्स होने चाहिए? कितने रूट्स होंगे? 4 होंगे। ठीक है, अब देखिए मिरर का क्या मतलब है। मिरर का मतलब ये है, देखिए अगर यहां पे एक मिरर अक्रॉस द ऑरिजिन, मिरर अक्रॉस द ऑरिजिन, ठीक है, पहले आप लोगों ने ऑटोकैड वगैरह में मिरर कमांड यूज की है ना?
यस सर।
ठीक है, सो इमेजिन करें कि हमारा एक्स एक्सिस या रियल एक्सिस जो है वो एक मिरर है, और मेरे यहाँ पे एक वो आ जाए, क्या कहते हैं, पोल आ जाए, रूट आ जाए। ठीक है, तो इसका मिरर इमेज कहाँ पे बनेगा? अगर ये आपका मिरर है, ये if the real axis is your mirror, इसका मिरर इमेज यहाँ पे बनेगा ना? ठीक है, अगर जो वर्टिकल एक्सिस है, इमेजिनरी एक्सिस है, अगर वो उसको आप मिरर कंसिडर कर लें, तो फिर इस रूट या हाँ इस रूट का मिरर इमेज फिर कहाँ पे बनेगा?
सेकंड प्लेन।
ठीक है, यहाँ पे बनेगा। ये डिस्टेंस सेम होगा, ये डिस्टेंस सेम होगा, लेकिन यहाँ पे बनेगा। ठीक है, जब हम कहते हैं मिरर अक्रॉस द ऑरिजिन, तो मिरर अक्रॉस द ऑरिजिन का मतलब ये, अगर जब आपकी प्रैक्टिस हो जाए फिर तो हम डायरेक्टली कर सकते हैं, लेकिन मिरर अक्रॉस द ऑरिजिन का मतलब ये है कि इट इज मिरर अक्रॉस बोथ द एक्सिस, बोथ द एक्सिस का मिरर इमेज है। सो फॉर एग्जांपल अगर ये एक्स है, इसका मिरर अक्रॉस द रियल लें तो ये वाला बनता है। अगर मिरर अक्रॉस द वाई लें तो ये वाला बनता है। मिरर अक्रॉस द ऑरिजिन कैसे होगा कि पहले आप अक्रॉस वन एक्सिस लें, तो अक्रॉस वाई एक्सिस ये आ गया, और फिर जो मिरर आया है उसका अक्रॉस एक्स एक्सिस दोबारा लेने, तो फिर हम कहते हैं कि ये डबल मिररिंग है ना, दोनों एक्सिस पे हमने मिररिंग किया, तो ये वाला इसका मिरर इमेज है। समझ आ रही है इस बात की?
Yes.
मिरर इमेज अक्रॉस द ऑरिजिन। ठीक है, सो मिरर इमेज अक्रॉस द ऑरिजिन, अगर हम दूसरी तरफ से भी स्टार्ट करें, पहले हम अक्रॉस द एक्स एक्सिस इसका मिरर इमेज ले लें, और फिर ये जो मिरर है इसका अक्रॉस द वाई ले लें, तो फिर भी हमारे पास वही मिरर इमेज अक्रॉस द ऑरिजिन आएगा। इट डजंट मैटर कि पहले आप एक्स का मिरर लेते हैं या वाई का मिरर लेते हैं। ठीक है, आप समझ आ रही है इस बात को?
यस सर।
ठीक है, अब मिरर इमेज अक्रॉस द ऑरिजिन हम लेते हैं अगर हमारे पास एक एक्सिस पे पड़ा अक्रॉस द ऑरिजिन, तो पहले हम अक्रॉस वाई लेते हैं, इसका मिरर यहां पे आ जाएगा। ठीक है, अब ये जो मिरर इमेज मेरे पास आ गया, ये तो खुद रियल एक्सिस पे है ना। अब रियल एक्सिस के अक्रॉस में इसका मिरर लूं तो वो भी यहीं पे आएगा, अपनी जगह पे ही आएगा। क्लियर है ना?
यस सर।
Yes, sir.
ठीक है, तो मिरर, तो ये अब ये दोनों जो है नॉट ओनली मिरर इमेज अक्रॉस द ओरिजिन है बट आल्सो मिरर इमेज अक्रॉस द वो भी है वर्टिकल एक्सिस भी, ठीक है। अब देखें रूल क्या है, मैथमेटिक्स ये अलजेब्रा का रूल है, इट डजंट हैव एनीथिंग टू डू विद कंट्रोल। कंट्रोल में इसकी इम्प्लीकेशंस हैं, लेकिन कंट्रोल वालों ने ये रूल नहीं बनाया। दिस इज मैथमेटिक्स रूल। मैथमेटिक रूल सेज दैट इफ यू हैव ए प्योर इवन पॉलिनोमियल, चाहे वो 4 डिग्री इवन पॉलिनोमियल है, 2nd डिग्री इवन पॉलिनोमियल है, 6 डिग्री इवन पॉलिनोमियल है, 100 डिग्री इवन पॉलिनोमियल है, देन all roots will have mirror image across, at least one mirror image across the origin. जैसे हमने कम्प्लेक्स नंबर का रूल है ना, कम्प्लेक्स नंबर का रूल ये है कि इफ यू हैव ए कम्प्लेक्स नंबर with an imaginary portion, then you will always have a conjugate of that complex number, ठीक है। मतलब अगर आपके पास एक कम्प्लेक्स रूट आता है तो बेस्ड ऑन द कम्प्लेक्स नंबर अलजेब्रा हमारे पास मैथमेटिक्स का रूल क्या है कि अगर आपके पास एक कम्प्लेक्स रूट आ गया तो उसका एक कम्प्लेक्स कंजुगेट जरूर आएगा। ये मैथमेटिक्स का रूल है, दिस इज नॉट, कंट्रोल वालों ने ये इजाद नहीं किया, ठीक है। इसी तरह मैथमेटिक्स का एक और रूल है कि अगर आपके पास इवन पॉलिनोमियल है तो उसके जो रूट्स होंगे दे विल ऑलवेज हैव मिरर इमेज अक्रॉस द ओरिजिन। ये भी मैथमेटिक्स का रूल है, ठीक है। अब कंट्रोल सिर्फ हमें ये कह रहा है, कंट्रोल हमें ये कह रहा है कि अगर तो ये 0 आ जाए तो इसका मतलब यह है कि जो ऊपर वाली पॉलिनोमियल है वो प्योर इवन पॉलिनोमियल है, और ए पॉलिनोमियल कंटेनिंग अ प्योर इवन पॉलिनोमियल। ये बस इतनी बात इसने आपको बता दी है ना, इतनी बात, प्योर इवन पॉलिनोमियल फैक्टर है। कंट्रोल रॉ स्टेबिलिटी टेबल जब 0 आ जाता है तो रॉ स्टेबिलिटी वाले कंट्रोल वाले बंदे आपको सिर्फ इतना कहते हैं कि ये जो 0 से ऊपर वाली जो पॉलिनोमियल है इट इज ए प्योर इवन polynomial factor of the actual starting polynomial, उसका प्योर इवन पॉलिनोमियल है, फैक्टर है। बस ये बात उसने बता दी, बाकी कंट्रोल वाले आपको कोई और नहीं बताया। अब आपने अपने मैथमेटिक्स का नॉलेज यूज करना। मैथमेटिक्स ये कहता है कि भाई अगर ये वाली इफ दिस इज फैक्टर ऑफ दिस पॉलिनोमियल तो इस पॉलिनोमियल के जो रूट्स होंगे वो इस पॉलिनोमियल के रूट्स के सेम होंगे, इस पॉलिनोमियल के जो रूट्स होंगे वो इस पॉलिनोमियल के भी रूट्स होंगे, क्योंकि दिस पॉलिनोमियल इज फैक्टर ऑफ दिस पॉलिनोमियल। क्लियर?
यस,
ठीक है। अच्छा, और मैथमेटिक्स आपको क्या कहता है? दूसरी बात मैथमेटिक्स आपको क्या कहता है? मैथमेटिक्स ये कहता है कि अगर आपके पास जब कभी प्योर इवन पॉलिनोमियल होगा तो इस प्योर इवन पॉलिनोमियल के जो रूट्स होंगे दे विल ऑलवेज सेटिस्फाई द कंडीशन ऑफ मिरर इमेज अक्रॉस द ओरिजिन। ठीक है,
राइट,
ठीक है। अब बस अब आपको क्लियर हो जाना चाहिए। फॉर एग्जांपल अगर मेरे पास एक इवन पॉलिनोमियल है s स्क्वायर प्लस मिसाल के तौर पे 4, ठीक है, मेरे पास ये आ जाता है और इज इक्वल टू 0, ये मेरे पास। तो मेरे पास इवन पॉलिनोमियल की कंडीशन क्या है कि the roots of even polynomial will always be mirror image across the origin। तो अगर मैं इसके रूट्स ले लूं, लेट्स चेक इट, इसके रूट ले लूं तो s इज इक्वल टू -4 आ जाएगा, और वो ले लूं तो s इज इक्वल टू प्लस माइनस 2 आयोटा, यही होगा ना?
यस सर।
एक ऊपर आ गया और एक नीचे आ गया। Does it satisfy the condition that the two roots are mirror image across the origin?
यस सर।
यस सर।
ठीक है। अच्छा, कोई और कंडीशन ले लें, चले s इज इक्वल टू -4 ले लें, ठीक है। सो s स्क्वायर इज इक्वल टू प्लस माइनस 2 हो जाएगा,
यस सर।
ठीक है, सॉरी s इज इक्वल टू प्लस माइनस 2 हो जाएगा। तो अगर एक जो है +2 पे आ जाए और दूसरा जो है -2 पे आ जाए, तो आर दे मिरर इमेज अक्रॉस द ऑरिजिन है?
यस सर।
सो इट इज सेटिस्फाइड, ठीक है। अच्छा, अब मेरे पास इस वक्त मैटलैब एक्सेस नहीं है, बट इफ वी हैव लेट्स सपोज s4 प्लस 2s² प्लस 4 इज इक्वल टू 0। अब हमारे पास 4 रूट्स होंगे, s1, s2, s3 and s4. Now all these four roots have to satisfy the conditions. वो conditions कौन से हैं? Condition number 1, that the roots will be mirror image across the origin. Condition number 2, that the roots, ठीक है, बस एक ही condition है फिलहाल। So पॉसिबिलिटी ये है कि फॉर एग्जांपल अगर मैं कहूं कि भाई मेरे तमाम रूट्स जो हैं वो रियल एक्सिस पे एग्जिस्ट करते हैं, तो अगर एक मैं यहां पर डाल दूं तो मुझे मजबूरन उसका मिरर इमेज एक यहां पे डालना पड़ेगा, ठीक है। अगर दूसरा मैं यहां पर डाल दूं तो मजबूरन उसका मिरर इमेज मुझे यहां पे डालना पड़ेगा। सो दैट टेल्स मी कि दिस सिस्टम, अगर उसमें से एक रूट भी रियल एक्सिस पे आ जाए तो बिकॉज ऑफ द कंडीशन के इसका मिरर इमेज जरूर होगा अक्रॉस द ऑरिजिन। इसका मतलब ये है कि अगर आपको एक रूट भी पता चल जाए कि रियल एक्सिस पे आ रहा है, तो इसका मतलब है कि ये सिस्टम अनस्टेबल, क्योंकि इसका एटलीस्ट जो एक जो है रियल एक्सिस पे आ रहा है उसका दूसरा जो है दूसरे साइड की रियल एक्सिस पे आएगा। इस बात की समझ आ रही है?
यस सर।
ठीक है। फॉर एग्जाम्पल पहले रूट,
अगर रियल,
जी कहें क्वेश्चन,
मतलब रियल पे भी अगर हमारे पास अगर रियल रूट आ गया तो बस मतलब सिस्टम अनस्टेबल
होगा, क्योंकि अगर आपके पास पहले और दूसरा रूट आ जाए ना, तो जो बाकी 2 रूट आ गए वो कहीं और नहीं हो सकते, वो इन 2 रूट्स के मिरर इमेज अक्रॉस द ऑरिजिन जरूर होंगे। ये कंडीशन है मैथमेटिक्स की, अलजेब्रा की कंडीशन है। तो मिरर इमेज कब बनेगा? अगर 2 यहां पर आ गए लेफ्ट हैंड साइड पे, तो इसका मिरर इमेज कहां पे बनेगा? राइट हैंड साइड पे बनेंगे। तो मैथमेटिक्स जो है आपको इन्फोर्स कर रहा है, मैथमेटिक्स आपको रिस्ट्रिक्ट कर रहा है कि देयर इज नो पॉसिबिलिटी कि दिस सिस्टम कैन बी स्टेबल। एनी सिस्टम which has even polynomial factor, and out of those even polynomial, if any one factor is on the real axis, any one root is on the real axis, the other one will be mirror image of that root, ठीक है। अच्छा, in case आपके पास एक रूट, 4 में से सिर्फ एक रूट मुझे पता चल जाए, 4 में से चले मुझे एक रूट का पता चल जाए, 4 में से अगर एक रूट का पता चल जाए, तो फॉर एग्जांपल मेरे पास एक रूट आ जाता है -2, बस मैं तो खुश हूं कि ठीक है, शुक्र है, सिस्टम तो स्टेबल अब तक नजर आ रहा है। लेकिन अगर एक -2 पे आ गया तो इसका मिरर इमेज कहां पे आएगा?
राइट साइड पे सर।
राइट साइड पे कहां पे आएगा? +2 पे आएगा। तो अगर एक भी स्टेबल मुझे पता चल जाए, मुझे पता है कि इसका जो मिरर इमेज है वो अनस्टेबल है, और ये सिस्टम जो है वो हो गया है, क्या कहते हैं, पूरा का पूरा सिस्टम अनस्टेबल हो गया। अच्छा, इमेजिन करें, फिर आपके ख्याल में ये क्वेश्चन भी हो सकता है कि सर ऐसे भी हो सकता है कि एक सिस्टम -2 पे चले, एक सिस्टम -2 पे, और दूसरा सिस्टम जो है फॉर एग्जांपल आपके पास कैलकुलेशन के दौरान आ जाता है 2 + 3 आयोटा पे आ जाता है। नाउ दिस इज रॉन्ग, आपकी कैलकुलेशन में गलती है। क्यों? देखिए, अगर एक -2 है तो उसका जो मिरर इमेज जो है +2 पे आएगा, ठीक है। दूसरा जो है -2 + 3 पे आ रहा है, यहां पे आ रहा है -2 और ये +3 पे आ रहा है। तो कॉम्प्लेक्स नंबर कंजुगेट के बगैर एग्जिस्ट नहीं कर सकता, ठीक है। कॉम्प्लेक्स नंबर कंजुगेट के बगैर एग्जिस्ट नहीं कर सकते हमारे जो डिफरेंशियल इक्वेशन में जब हम रूट्स निकालते हैं, ठीक है। तो इसका मतलब है बेस्ड ऑन द कॉम्प्लेक्स कंजुगेट रिक्वायरमेंट इसका एक रूट यहां पे होगा, तो 1 2 3 4 रूट हो गए, ठीक है। लेकिन हमें इवन पॉलिनोमियल की रिक्वायरमेंट यह है कि इस रूट का फिर एक मिरर इमेज यहां पर भी होगा और इस रूट का एक मिरर इमेज यहां पर भी होगा। सो पॉसिबिलिटी चार रूट्स जो है इवन पॉलिनोमियल के चार रूट्स की सिर्फ तीन पॉसिबिलिटीज है, ये या ये या ये। समझ आ रही इस बात की?
यस सर।
क्योंकि इन तीनों पॉसिबिलिटीज में हम तमाम कंडीशन सेटिस्फाई कर रहे हैं मैथमेटिक्स की, अलजेब्रा की कंडीशन। कंडीशन नंबर 1 फॉर इवन पॉलिनोमियल के roots will always be mirror image across the origin. Condition number 2 of complex numbers, that a complex number can exist in the complex plane only if it has a conjugate or करें कि भाई ये इसका mirror image across the origin है और at the same time these two are complex conjugate of each other. So आप तमाम कंडीशन को सेटिस्फाई करें तो ये पॉसिबिलिटी पॉसिबल है, अदरवाइज नहीं। अब ना ठीक है, जो मैं समझाने की कोशिश कर रहा हूँ मैंने अपनी तरफ से कर लिया। अब कंफ्यूजन है, ये किसी मुझसे पूछ सकते हैं।
सर ये सब कुछ हमने किस चीज के लिए सर किया?
ये सब कुछ हमने किस, वेरी गुड क्वेश्चन। चलें, समटाइम्स सिंपल क्वेश्चन इज द बेस्ट क्वेश्चन। ठीक है, थैंक यू। ये हमने इसलिए किए हैं, ये हमने इसलिए किए हैं। 0 0 कहाँ पे आ रहा है? ये आ रहा। चले, माय क्वेश्चन नंबर 1 मैं आपसे पूछता हूँ, इसको देखें। खैर दिस इज नॉट एग्जाम, ठीक है, इज इंटरैक्टिव डिस्कशन। इस टेबल को देखें, रॉ स्टेबिलिटी टेबल बनाया गया है, ठीक है। इस एस टर्म को रिप्लेस करके इसकी जगह उसके डिराइवेटिव, इस टर्म का डिराइवेटिव यहाँ पे लगा दिया, इस टर्म का डिराइवेटिव यहाँ पे लिख दिया गया है, ठीक है। नाउ वी इंटरप्रेट द रॉ स्टेबिलिटी टेबल, ठीक है। फर्स्ट कॉलम में नंबर ऑफ साइन चेंजेस कितने?
0
zeros, ठीक है। सो हाउ मेनी, नाउ माय क्वेश्चन फ्रॉम यू इज, this is a fifth degree polynomial, so number of poles, closed loop poles कितने हैं? Number 1. number of poles, closed loop poles in left hand plane कितने हैं? number of closed loop poles on imaginary axis कितने? number of closed loop poles in right hand plane कितने? ये जवाब आप रॉ स्टेबिलिटी क्राइटेरिया से दे सकते हैं। देखिए अब तक हमने क्या डिस्कस किया था, मैंने कहा कि आप रॉ स्टेबिलिटी क्राइटेरिया से ये बता सकते हैं कि ये सिस्टम स्टेबल है अनस्टेबल है। अगर एक साइन चेंज भी है तो इसका मतलब है कि इसमें से एटलीस्ट एक जो है वो रूट राइट हैंड प्लेन में। फिर मैंने आपको ये कहा कि आप रॉ स्टेबिलिटी टेबल से ये भी मालूम कर सकते हैं कि फॉर व्हाट रेंज ऑफ के द सिस्टम इज स्टेबल एंड फॉर व्हाट रेंज ऑफ के द सिस्टम इज अनस्टेबल। अब मैं आपसे ये कह रहा हूँ कि आप रॉ स्टेबिलिटी टेबल से आप ये भी मालूम कर सकते हैं कि जो टोटल पोल्स हैं, आप ये नहीं बता सकते कि पोल की एग्जैक्ट लोकेशन क्या है, लेकिन आप ये बता सकते हैं कि पोल, ये जो 5 पोल्स हैं इनमें से कितने पोल राइट हैंड प्लेन में, कितने पोल उसमें लेफ्ट हैंड प्लेन में, कितने पोल जो है इमेजिनरी एक्सिस के ऊपर। ठीक है, अब मैं आपसे पूछ रहा हूं, अब मैं आपसे क्वेश्चन पूछ रहा हूं, टोटल नंबर ऑफ पोल्स कितने हैं? 5। इस पॉलिनोमियल को देख के बताएं। 5 सर, बिल्कुल सही। टोटल नंबर ऑफ पोल्स आर 5। ठीक है, अब मुझे ये बात बताएं कि लेफ्ट हैंड प्लेन में कितने पोल्स हैं? कोई अनस्टेबल प्लेन है, पोल है इस केस में?
सर सारे पॉजिटिव है तो सारे लेफ्ट हैंड में,
सारे लेफ्ट हैंड में
सिवाय एक्सेप्ट द वन।
इसमें एक वो है प्योर इवन पॉलिनोमियल है।
वेरी गुड, वेरी गुड, वेरी गुड। अब आते हैं, लेट मी आस्क यू दिस क्वेश्चन। पहले मुझे बताएं कि राइट हैंड प्लेन में कोई है पोल? हैंड प्लेन इमेजिनरी एक्सिस और लेफ्ट हैंड प्लेन। राइट हैंड प्लेन में कितने पोल्स हैं ये बताएं। अनस्टेबल पोल्स कितने? 0,
एक ही होता है जो
because there is no sign change, so there are 0 poles in the right hand plane. अब 5 total poles हैं। अब do we know that all the 5 planes are in the left hand plane?
No, sir.
We don't know. ठीक है? But we do know that two of the pole are from the pure even polynomial. Pure even polynomial. ठीक है? दो पोल्स जो प्योर इवन पॉलिनोमियल से, अगर दो पोल्स प्योर इवन पॉलिनोमियल से हैं, then they have to follow the restriction that both the poles must have their mirror image across the origin. तो अगर एक पोल मिसाल के तौर पे मैं यहाँ पे डालूं तो मुझे तो दूसरा पोल यहाँ पे डालना पड़ेगा, जो कि पॉसिबल नहीं है, क्योंकि मुझे रॉ स्टेबिलिटी की साइन चेंज से पता है कि राइट हैंड प्लेन में कोई पोल नहीं, तो इसका मतलब है कि मैं यहाँ पर नहीं हो सकता। ठीक है। सेकंड, अगर मैं यहां पर डाल दूं तो मुझे एक कॉम्प्लेक्स कंजुगेट यहां पे डालना पड़ेगा, तो 2 पोल्स हो गए, और साथ में मुझे मिरर इमेज अक्रॉस द ऑरिजिन भी डालना पड़ेगा। तो फिर तो मुझे पता चले कि 2 पोल्स राइट हैंड प्लेन में होंगे, लेकिन राइट हैंड प्लेन में तो 0 है, तो ये भी पॉसिबल नहीं है। ठीक है। नेक्स्ट, अगर मैं यहां पर डाल दूं तो इसका मिरर इमेज अक्रॉस द ऑरिजिन यहां पे आएगा। ठीक है। तो इसका मतलब ये है कि राइट हैंड पे तो नहीं आ रहा, तो इसका मतलब है कि 2 जो है आउट ऑफ 5 2 ऑफ द पोल्स आर ऑन द इमेजिनरी एक्सिस। बाकी कितने रह गए? 3। तो 3 जो है आपके लेफ्ट हैंड प्लेन। Now let's make it a little bit interesting. Imagine this row becomes 0. ठीक है। This row becomes 0 and there is two sign changes. 2 sign changes. अब दोबारा इसी प्रॉब्लम को सॉल्व करते हैं, इंटरप्रिटेशन करते हैं। अगर s क्यूब जो है 0 है तो इसका क्या मतलब है कि s4 जो है, ठीक है, लेट्स सपोज देयर इज a 6 as well, 2 3 4 7, अदरवाइज ये प्रॉब्लम गलत हो जाएगी। ठीक है। Now, if S4 is pure even polynomial, तो इसका मतलब है कि 4 पोल्स ऐसे हैं इस सिस्टम के जो कि, तो this is basically, let's suppose 6S6. This is 6 degree polynomial. Total number of poles 6 हो गए, उसमें से 2 साइन चेंजेस हैं, तो 2 तो अनस्टेबल हो गए। ठीक है। 2 अनस्टेबल हो गए और हमारे पास 4 डिग्री पॉलिनोमियल जो है वो प्योर इवन पॉलिनोमियल है। तो हमारे पास 4 पोल्स ऐसे होंगे, 4 पोल्स ऐसे होंगे कि जो कि ऑरिजिन मिरर इमेज अक्रॉस द ऑरिजिन होंगे, और वो हमारे पास सिर्फ 2 पॉसिबिलिटीज है। एक पॉसिबिलिटी ये है और दूसरी पॉसिबिलिटी ये है। तो इन 2 पॉसिबिलिटीज में से हमने सेलेक्ट करना है कि कौन सी पॉसिबिलिटी इस पर्टिकुलर केस के लिए एग्जिस्ट करती है। तो अगर हम ये वाली पॉसिबिलिटी, ठीक है, अच्छा, तो यहां पर थोड़ी सी कैलकुलेशन नहीं की, नंबर ऑफ जिसके हिसाब से डिफरेंट होगी। इफ दिस पॉसिबिलिटी, सेलेक्ट दिस पॉसिबिलिटी, बस 4 जो है इमेजिनरी एक्सिस पे आ जाएंगे, एंड वी हैव टू पुट 2 in the right hand plane। और अगर हमारे पास हम ये दूसरी पॉसिबिलिटी सेलेक्ट कर लें तो हमारे पास ये सिचुएशन आएगी। इस बात की समझ आ रही स्टूडेंट्स?
यस सर।
इन शॉर्ट क्या मेरा मतलब, इन शॉर्ट आपके पास अगर इवन पॉलिनोमियल आ गया तो प्योर इवन पॉलिनोमियल आ गया। प्योर अगर एक, चलिए स्टार्ट, अगर रॉ स्टेबिलिटी टेबल बनाते वक्त कोई ऑड लाइन आपके पास, ऑड पावर लाइन रो जो है वो 0 आ जाए, तो इससे ऊपर वाली जो रो होगी वो हम इसका मतलब ये कि इससे ऊपर वाली जो इवन रो है, इट इज अ प्योर इवन पॉलिनोमियल फैक्टर ऑफ द क्लोज्ड लूप पॉलिनोमियल कैरेक्टरिस्टिक ऑफ द क्लोज्ड लूप कैरेक्टरिस्टिक पॉलिनोमियल। एक दफा ये है तो इसका मतलब ये है कि ये जो इवन पॉलिनोमियल है इसके जो रूट्स हैं वो इस क्लोज्ड लूप पॉलिनोमियल के रूट्स भी हैं, लेकिन एक एडिशनल कंडीशन इन रूट्स के ऊपर है, सिर्फ इसकी कंडीशन पॉलिनोमियल की जो रूट्स है वो हमेशा हमेशा मिरर इमेज अक्रॉस द ओरिजिन होती है, ठीक है। Once you know this additional information, you can use information to figure out what kind of system response, right hand, how many poles are in the left hand plane, how many poles are on the imaginary axis. So this is an additional information. अब मैं इसका आखिरी खुलासा करता हूँ। आज की क्लास में हमने क्या पढ़ा कि हमें raw stability analysis, अगर आपके पास सिंपल ट्रांसफर फंक्शन है उसकी स्टेबिलिटी एनालिसिस आप आसानी से कर सकते हैं। अगर आपके पास एक क्लोज लूप फीडबैक कंट्रोल सिस्टम है उसकी भी स्टेबिलिटी एनालिसिस आप आसानी से कर सकते हैं, लेकिन अगर उस फीडबैक कंट्रोल सिस्टम के अंदर कोई एक वेरिएबल है जिसकी वजह से क्लोज लूप ट्रांसफर फंक्शन, उस वेरिएबल वैल्यू की चेंज की वजह से क्लोज लूप ट्रांसफर फंक्शन की कैरेक्टरिस्टिक इक्वेशन चेंज होती है, तो फिर उस सिस्टम की एनालिसिस, स्टेबिलिटी एनालिसिस करने के लिए या तो आप रॉ स्टेबिलिटी क्राइटेरिया यूज करेंगे या आप रूट लोकस यूज करेंगे। एक दो और मेथड भी हैं, लेकिन हमारे कोर्स में ये दो मेथड है। आज के लेक्चर में हमने रॉ स्टेबिलिटी क्राइटेरिया पर, रॉ स्टेबिलिटी क्राइटेरिया के 3 स्टेप्स है। स्टेप नंबर 1, फाइंड द क्लोज लूप ट्रांसफर फंक्शन, क्योंकि रॉ स्टेबिलिटी क्राइटेरिया हम सिर्फ क्लोज लूप फीडबैक कंट्रोल सिस्टम के लिए इस्तेमाल करते हैं। क्लोज लूप ट्रांसफर फंक्शन का आप कैरेक्टरिस्टिक पॉलिनोमियल मालूम करें, उससे टेबल बनाएं, टेबल्स बनाने के बाद जो है उसको इंटरप्रेट करके आप बताएं whether the system is stable, unstable, or for what value of the variable k the system remains stable, or for what value it remains unstable। फिर हमने 2 स्पेशल केसेस पढ़े। रॉ स्टेबिलिटी का मेथड यहाँ तक पूरा हो गया, लेकिन उसके 2 स्पेशल केसेस हैं। केस नंबर 1, अगर फर्स्ट कॉलम में सिर्फ फर्स्ट कॉलम में अगर 0 आ जाए, इसको कैसे डील करेंगे वो तो हमने सिंपल किया कि उसको हमने रिप्लेस कर दिए बाय एप्सिलॉन, वेयर एप्सिलॉन इज अ पॉजिटिव very small positive number approaching to 0। Case number 2 क्या है कि if the whole row becomes equal to 0, if the whole row becomes 0, इसका मतलब कि इससे ऊपर वाली जो रो है वो परफेक्ट फैक्टर है, वो परफेक्ट फैक्टर है कैरेक्टरिस्टिक पॉलिनोमियल का। तो इसका मतलब से जो इससे ऊपर वाली रो है उसके जो रूट्स होंगे वो रूट्स कैरेक्टरिस्टिक पॉलिनोमियल के भी रूट्स होंगे। सिर्फ एक चीज का आपने ख्याल रखना है कि अगर आपका जो परफेक्ट फैक्टर आ रहा है, अगर वो इवन पॉलिनोमियल है, तो इवन पॉलिनोमियल में अलजेब्रा के रूल्स ये हैं कि इवन पॉलिनोमियल के जो रूट्स होते हैं वो हमेशा मिरर इमेज अक्रॉस द ओरिजिन होते हैं। बस नाउ दिस एडिशनल इंफॉर्मेशन को यूज करके आप बता सकते हैं कि इस सिस्टम के, वैसे नॉर्मली रॉ स्टेबिलिटी क्राइटेरिया तो आपको सिर्फ ये बताता है कि राइट हैंड प्लेन में कितने पोल्स हैं, with that is equal to number of sign changes in the first column of the raw stability table। लेकिन अगर आपको ये एडिशनल इंफॉर्मेशन मिल गई है इवन पॉलिनोमियल की, तो उससे आप बता सकते हैं, ना सिर्फ ये बता सकते कि राइट हैंड प्लेन में कितने रूट्स हैं कैरेक्टरिस्टिक पॉलिनोमियल के, बल्कि आप ये भी बता सकते हैं कि लेफ्ट हैंड प्लेन में कितने रूट्स हैं कैरेक्टरिस्टिक पॉलिनोमियल के, और आप ये भी बता सकते हैं कि इमेजिनरी एक्सिस पे कितने रूट्स हैं कैरेक्टरिस्टिक पॉलिनोमियल के। ये सारे जो है आप बता सकते हैं। ठीक है, एनी क्वेश्चन?
सर एक अच्छा सा एग्जांपल है सर इस स्लाइड में, ताकि हमें और भी क्लियर हो जाए।
स्लाइड में सिंपल रॉ स्टेबिलिटी क्राइटेरिया करते हैं किस चीज को?
हाँ सर, ये जो रो जीरो, पूरी रो जो 0 हो जाए सर, उससे हम किस सारे लोकेशंस का पता
अच्छा, मेरे पास देखिए सिर्फ एक यही एग्जांपल है, बुक में शायद और भी हो, मेरे पास यही एक है। सो डू यू वांट टू दोबारा इसको देखना चाहते हैं एक नजर?
यस सर, एक बार ये बता दें सर, ये लोकेशंस
मेरे पास
फाइंड कर।
दूसरा प्रॉब्लम नहीं है, ठीक है। सो ओके, आपको मिसाल के तौर पे एक कैरेक्टरिस्टिक पॉलिनोमियल गिवन है क्लोज लूप ट्रांसफर फंक्शन का, और आपसे कहा जाता है कि इसका राव स्टेबिलिटी, इसकी राव स्टेबिलिटी एनालिसिस करें। लेकिन सिर्फ ये ना बताएं कि ये सिस्टम स्टेबल है या अनस्टेबल, बल्कि ये बताएं कि लेफ्ट हैंड प्लेन में कितने पोल्स हैं और इमेजिनरी एक्सिस पे कितने पोल हैं और राइट हैंड प्लेन में कितने पोल हैं। Now we know since the characteristic polynomial is a fifth degree polynomial, so total number of poles कितने, number of closed loop poles is equal to 5. अब हमें डिसाइड करना है कि इसमें कितने राइट हैंड प्लेन पे, कितने लेफ्ट हैंड प्लेन में, कितने इमेजिनरी एक्सिस पे। ठीक है, फ्रॉम द टेबल की जो बेसिक इंटरप्रिटेशन है, अगर उस बेसिक इंटरप्रिटेशन को हम देखें तो कोई भी पोल जो है राइट हैंड प्लेन में नहीं। ठीक है, अगर कोई भी पोल राइट हैंड प्लेन में नहीं है क्योंकि कोई साइन चेंज नहीं हुआ, तो यहाँ पे तो जीरो आ गया। ठीक है, अगर जीरो आ गया तो बाकी जो 5 पोल्स रह गए हैं, तो 5 पोल्स या तो सारे के सारे राइट हैंड प्लेन में, या सारे के सारे इमेजिनरी एक्सिस पे, या उसमें से कुछ इमेजिनरी एक्सिस पे, कुछ राइट हैंड प्लेन पे, तो सॉरी लेफ्ट हैंड प्लेन में। थैंक यू। ठीक है, अब जब हम ये टेबल बना करूं कि वो तो सिंपल है। डू यू वांट मी टू डिस्कस?
नो सर, दैट्स
ठीक है, तो अब मैं क्या कर दूं कि आई जस्ट रियलाइज कि मेरे पास इनिशियली ये एस की रो तो जीरो थी, इनिशियली तो जीरो थी। ये जो एस की रो में 6 और 0 मैंने लिखा है, ये तो एक्चुअल कैलकुलेशन से नहीं आया था, ये तो मैंने जो डिराइवेटिव लिया तो फिर मेरे पास 6 और 0 आया। ठीक है, तो इसका मतलब ये है कि ये वाली जो रो है विच इज एन इवन पॉलिनोमियल, ठीक है, इट इज अ परफेक्ट फैक्टर, इट इज अ परफेक्ट फैक्टर ऑफ दिस, ये वाले या ये पॉलिनोमियल, दिस पॉलिनोमियल इज अ फैक्टर ऑफ दिस पॉलिनोमियल। तो इसका मतलब है कि अगर इस पॉलिनोमियल के रूट्स में निकाल लूं, अगर इस पॉलिनोमियल के रूट्स में निकाल लूं, तो वही रूट्स इस कैरेक्टरिस्टिक पॉलिनोमियल के भी रूट्स होंगे।
राइट।
ठीक है, तो अगर देखूं तो मैं डायरेक्टली, ये तो सिंपल कैलकुलेशन है ना, क्योंकि ये देखिए ये क्या हो जाएगा, एस स्क्वायर इज इक्वल टू 4 हो जाएगा, -4 हो जाएगा, और ये जो हो जाएगा एस स्क्वायर इज इक्वल टू ±2 आयोटा हो जाएगा। तो डायरेक्टली भी मुझे पता चल गया कि दो जो है रियल एक्सिस पे, सॉरी इमेजिनरी एक्सिस पे, कैलकुलेशन से भी मुझे पता चल गया। ठीक है, लेकिन मैं दूसरे तरीके से भी मालूम कर सकता हूँ, मैं दूसरे तरीके से मालूम ऐसे कर सकता हूँ कि मुझे पता है कि इस पॉलिनोमियल के जो रूट्स हैं दे हैव टू फॉलो द मिरर इमेज अक्रॉस द ओरिजिन का जो रूल है उसको फॉलो करें। तो अगर मैं मिसाल के तौर पे मेरे पास 3 पॉसिबिलिटीज हैं, ब्रॉडर कैटेगरीज हैं। एक ये कि कम्प्लेक्स प्लेन के अंदर अगर रूट हो, तो अगर कम्प्लेक्स प्लेन के अंदर एक रूट आ जाएगा तो इसका दूसरा रूट यहाँ पे होना चाहिए क्योंकि उसका कंजुगेट होना चाहिए, और फिर जो मिरर इमेज का रूल है अक्रॉस द ओरिजिन उसके हिसाब से एक यहाँ पे होना चाहिए और एक यहाँ पे होना चाहिए। तो अगर मैं एक रूट कम्प्लेक्स प्लेन के अंदर डाल दूं तो एक रूट से मेरा गुजारा नहीं चलेगा, 2 से भी मेरा गुजारा नहीं चलेगा, मुझे कम से कम 4 रूट्स चाहिए होंगे। ठीक है, तो ये तो पॉसिबल। इसका मतलब ये है कि अगर आपके पास सेकंड डिग्री इवन पॉलिनोमियल है, सो इट कैन नॉट एग्जिस्ट इन द कम्प्लेक्स प्लेन, इट कैन ओनली एग्जिस्ट ऑन द imaginary axis, or it can only exist on the imaginary axis or the real axis। इसके ऊपर एग्जिस्ट कर सकता है। क्यों? क्योंकि अगर रियल एक्सिस के ऊपर एक रूट में डाल दूं तो इस मिरर इमेज अक्रॉस द ओरिजिन क्या होगा कि दूसरा यहाँ पे आ जाएगा, तो मुझे किसी तीसरे या चौथे या 5वें रूट की जरूरत नहीं है अलजेब्रा की कंडीशन को सेटिस्फाई करने के लिए। तो इसका मतलब यह है कि मेरे पास अब सिर्फ 2 पॉसिबिलिटीज है, क्योंकि मेरे पास सेकंड डिग्री इवन पॉलिनोमियल है, या तो ये दोनों यू हैं या ये दोनों यू हैं। ठीक है, अगर
तो रियल तो नहीं हो सकते हैं क्योंकि राइट हैंड प्लेन में नहीं होना चाहिए।
बिल्कुल, अगर मैं ये इन 2 चॉइसों में अगर मैं ये वाली चॉइस सेलेक्ट करता हूँ तो वो तो मुझे फोर्स करता है कि आपका एक पोल जो है यहाँ पे आएगा राइट हैंड प्लेन में, लेकिन मुझे साइन चेंज से पता है कि राइट हैंड प्लेन में कोई पोल नहीं है। तो इसका मतलब है कि ये सिचुएशन नहीं है। इसका मतलब ये है कि दूसरी सिचुएशन मेरे पास क्या रहेगी कि इमेजिनरी एक्सिस पे हैं ये पोल। और अगर आप यहाँ पर देखें इस सिस्टम के जो दो पोल मैंने कैलकुलेशन से भी निकाले थे वो दोनों इमेजिनरी एक्सिस पे हैं। सो आप कैलकुलेशन से भी मालूम कर सकते हैं या आप लॉजिकल रीजनिंग करके, अलजेब्रा के रूल्स आपको पता है कि अगर कॉम्प्लेक्स प्लेन, देखिए ये हम कहते हैं कि ये वाला पोल इमेजिनरी एक्सिस के ऊपर है, ये वाला पोल इमेजिनरी एक्सिस, हम कहते हैं ये रियल एक्सिस के ऊपर है, ये रियल एक्सिस के ऊपर है। इस पोल को हम कहते हैं कि ये कॉम्प्लेक्स प्लेन के अंदर है, ये प्लेन के अंदर एक्सिस से निकल गया है, प्लेन के अंदर चला गया। इसका मतलब कि इसका रियल पार्ट भी है और इमेजिनरी पार्ट भी है। सो हमें पता है कॉम्प्लेक्स नंबर थ्योरी हमें यह बताती है कि अगर कॉम्प्लेक्स प्लेन के अंदर एक नंबर आ जाए या पोल आ जाए तो उसका कॉम्प्लेक्स कंजुगेट जरूर होना चाहिए, उसके बगैर वो एग्जिस्ट नहीं कर सकता कॉम्प्लेक्स प्लेन में। आपने अब तक जितने प्रॉब्लम किए होंगे, अगर कॉम्प्लेक्स प्लेन के अंदर पोल आ जाता है तो वो जरूर उसका कॉम्प्लेक्स कंजुगेट होगा। सेकंड चीज अभी हमने डिस्कस की है कि अगर आपके पास कोई इवन पॉलिनोमियल, प्योर इवन पॉलिनोमियल, तो उसके रूट जो हैं वो बाकी तमाम मैथ्स के रूल तो फॉलो करेंगे, लेकिन वो एक एडिशनल रूल को भी फॉलो करते हैं। वो एडिशनल रूल क्या है कि the roots of a even polynomial will always be mirror image across the origin. ठीक है ना। इस इंफॉर्मेशन को आप लॉजिकली इस्तेमाल करके इस बात का जवाब दे सकते हैं, क्योंकि अगर दो इमेजिनरी एक्सिस पे हो गए तो बाकी तीन कहां पे होंगे? लेफ्ट हैंड प्लेन पे।
यस सर।
ठीक है। अच्छा, एक और स्टूडेंट, चूंकि आप लोग समझने के शौकीन है, वो स्टूडेंट है जो कि क्लास के बाद बैठे हुए हैं। सो आई विल गिव यू सम अनदर, एक एडिशनल रूल, ठीक है, कहते हैं ना जैसे गेम्स में होता है एडिशनल पैक, क्या कहते हैं उसे? बोनस पैक। बोनस पैक ये है कि आपके एक क्वेश्चन ये भी आ सकता है कि सर व्हाट इफ ये वाली रो, मिसाल के तौर पे यहाँ पे S6 की भी रो और ये जो है 2, 3, 4 आ जाए मिसाल के तौर पे, और आप कहते हैं कि सर ये वाली रो, मिसाल के तौर पे ये वाली रो 0, 0 हो गई, मिसाल के तौर पे, ठीक है। इफ दिस इज द रो दैट इज 0, समझ आ रही इस बात की? तो फिर इसका मतलब यह है कि जो ऊपर वाली रो जो है, दिस इज परफेक्ट फैक्टर ऑफ दिस पॉलिनोमियल। यानी इससे पॉलिनोमियल बनाते हैं तो वो पॉलिनोमियल बनेगा 6.4 S³ प्लस 25.6 S प्लस 0। तो इसका मतलब है कि P ऑफ S इज ए परफेक्ट फैक्टर ऑफ D of S का परफेक्ट फैक्टर है। मीन्स कि D of S is equal to P of S multiply some other factor, let's call it B of S। ठीक है। तो इसका मतलब है कि P of S के जो रूट्स हैं वो जो हैं D of S के भी रूट्स हैं। क्लियर?
यस सर।
अब क्वेश्चन ये आता है कि सर देन हाउ डू वी ट्रीट प्योर ऑड पॉलिनोमियल को, कैसे ट्रीट करें? प्योर इवन पॉलिनोमियल के बारे में तो हमने आपसे एक चीज सीख ली है कि उसके जो रूट्स हैं हमेशा मिरर इमेज अक्रॉस द ऑरिजिन होंगे। तो क्या ऐसी कोई बात ऑड पॉलिनोमियल के लिए भी एग्जिस्ट करती है? सो दैट्स वेरी इंटरेस्टिंग। लेट्स टेक अ प्योर इवन पॉलिनोमियल। लेट्स टेक इट लेट्स सपोज 4x प्योर ऑड पॉलिनोमियल 4x5 प्लस 3x³ in terms of S करते हैं प्लस 2s प्योर इवन पॉलिनोमियल है ना स्टूडेंट्स?
यस सर।
अच्छा, प्योर इवन पॉलिनोमियल है। अब sorry, I'm sorry, odd polynomial, pure odd polynomial, ठीक है। Now if it is a pure odd polynomial, अब इसके लिए मैथमेटिक्स क्या कहती है? Mathematics says that every odd polynomial is basically a root एट ऑरिजिन मल्टीप्लाई इवन पॉलिनोमियल। देख लेना, इसमें से आप s कॉमन ले सकते हैं, s तो क्या बनेगा 4s4 प्लस 2s2 प्लस 2। समझ आई?
यस सर।
तो जो ऑड प्योर ऑड पॉलिनोमियल जो होता है ना, वो उसमें से अब आपके पास 5 रूट्स होंगे। एक रूट जो है s इज इक्वल टू 0, दिस इज इक्वल टू 0, ये ऑरिजिन पे, ये रूट जो है ऑरिजिन पे, और बाकी जो 4 जो रूल है उसको फॉलो करें। समझा?
यस सर।
ये अक्सर जब मैं बोर्ड पे कराता था तो स्टूडेंट ये क्वेश्चन पूछते थे कि सर आप तो कह रहे हैं कि हमेशा S1 रो जो है, जैसे इस केस में S रेज़ टू पावर 1 की रो 0 हो गई थी, या फॉर एग्जांपल S रेज़ टू पावर 3 की रो 0 हो जाए, ठीक है। व्हाट इफ S4 की पावर 0 हो जाए, या S0 की पावर, यहाँ पे तो खैर एप्सिलॉन हम डाल देंगे, ये इस तरह कोई और जो मतलब इवन रो 0 दे, तो इसका मतलब कि इससे ऊपर वाली ऑड रो जो है वो परफेक्ट फैक्टर है कैरेक्टरिस्टिक पॉलिनोमियल का, तो उसको हम कैसे ट्रीट करेंगे? तो उसका मैंने आपको जवाब दिया कि अगर आपके पास परफेक्ट ऑड रो आ जाए, इन केस, आई एम नॉट श्योर क्योंकि मैंने इस तरह के प्रॉब्लम देखे नहीं है, इन केस आ जाता है, मैथमेटिक्स पॉसिबिलिटी है, सो यू कैन ट्रीट इट, एवरी odd polynomial is basically a product of s equal to 0, a root at 0, multiply an even polynomial. ठीक है? Any question? That concludes everything. जितना मैं आपको कन्वे करना चाह रहा था इंफॉर्मेशन, वो सब के साथ कन्वे कर लिए। If there is any other question, confusion, I can discuss it with you.
सर मेरा एक क्वेश्चन था, जब हम प्रोपोर्शनल कंट्रोलर डिस्कस कर रहे थे, जब k की वैल्यू मालूम करते हैं, तो उसमें हमने जितने भी एग्जांपल किए उसमें सारे जो हमारे पास आ रहे थे पॉजिटिव साइंस आ रहे थे, जिसकी वजह से हमने k की जो वैल्यू थी उसको भी हमने पॉजिटिव करके k की वैल्यू मालूम। तो अगर इन केस हमारे पास कोई रूट जो है नेगेटिव आ जाता है तो उसमें फिर हम क्या करेंगे?
Just follow the mathematics. Just follow the mathematics. देखें, फॉर एग्जाम्पल आप मजबूर हो जाएं कि k की वैल्यू नेगेटिव होगी, तो आप उसके जवाब में ये कहेंगे कि द सिस्टम इज स्टेबल फॉर k वैल्यू लेस देन 0।
राइट,
ठीक है, मतलब नेगेटिव प्रोपोर्शनल भी हो सकता है, k की वैल्यू जरूरी नहीं है कि 0 टू इंफिनिटी हो, इट कैन बी फ्रॉम माइनस इंफिनिटी टू प्लस इंफिनिटी। ठीक है, या आप ये कह सकते हैं, आप इसको यूं जवाब दे सकते हैं कि द सिस्टम इज अनस्टेबल फ्रॉम 0 टू इंफिनिटी फॉर k वैल्यू इक्वल टू 0 टू इंफिनिटी। द ओनली वे वी कैन मेक the system stable if we use negative proportional controller. ठीक है, जो जिन स्टूडेंट ने क्वेश्चन पूछे थे क्लियर है? एनी अदर क्वेश्चन? और आपके बुक में ऐसे प्रॉब्लम्स हैं कि जिसमें मतलब है, यहाँ पे तो बड़े सिंपल से प्रॉब्लम है, वो भी इतने कोई कॉम्प्लिकेटेड नहीं है, लेकिन मेरा कहने का मतलब ये है कि उसमें से कुछ ऐसे प्रॉब्लम शायद मेरे पास यहाँ पर भी है, ये वाला प्रॉब्लम, हाँ इसमें एक चीज आती है। ठीक है, आप ये प्रॉब्लम देख लें, अगर इसमें इशू है तो नेक्स्ट क्लास में मुझे बता दें। इसमें बहुत बार ऐसे प्रॉब्लम आते हैं, एग्जाम में भी बुक में भी मौजूद है, जहां पे यहाँ पे क्वाड्रेटिक इक्वेशन आ जाए। ठीक है, अब उस क्वाड्रेटिक इक्वेशन को आप कैसे हैंडल करेंगे? ठीक है, उस क्वाड्रेटिक इक्वेशन को आप कैसे हैंडल करेंगे, ये पहले आप कोशिश करें, अगर आप नहीं कर सकते तो फिर मुझे बता दें। आप जो बुक में ऐसे प्रॉब्लम है, पिछले एग्जाम्स में भी ऐसे प्रॉब्लम आए हुए हैं जिसमें आपके पास क्वाड्रेटिक इक्वेशन आ जाए।
सर ये चैप्टर 6 में से है?
ये चैप्टर 6 है, बिल्कुल 6।
सर मतलब प्रॉब्लम चैप्टर 6 से है सर ये?
हाँ, ये नॉट श्योर अबाउट दिस प्रॉब्लम, लेकिन इसी तरह के प्रॉब्लम चैप्टर 6 में। ठीक है, इसी तरह के प्रॉब्लम है। आई एम नॉट श्योर दैट दिस इज एग्जैक्टली फ्रॉम द बुक। ठीक है, एनी अदर क्वेश्चन स्टूडेंट्स?
नो सर।
ठीक है, फिर मैं कंक्लूड करता हूँ आज का लेक्चर। Inshallah, I'll see you tomorrow at 2 o'clock.
Excuse me,
Okay,
sir.
thank you.
Sir, can you upload this lecture right now, sir? Because we have to look at it in the night, so we ourselves get
ठीक है, मैं थोड़ी
for
देर बाद
tomorrow class.
ठीक है, थोड़ी देर बाद मैं अपलोड करता हूँ। ठीक। बाकी आज का लेक्चर ये खत्म हो गया, नेक्स्ट लेक्चर थोड़ा सा डिफरेंट, वो नया टॉपिक होगा।
Okay, sir. All right. Thank you.
ठीक है, हाँ, अल्लाह हाफिज़।
Allah Hafiz, sir.
अल्लाह हाफिज़।